Let's take a journey into the past, to a time so distant that the very shape of our planet would be unrecognizable. Forget the familiar map of the world, where the Atlantic Ocean divides America and Europe, where Asia rises majestically above the Indian Ocean and Africa takes its rightful place. Let's travel to a time when none of this existed. Instead of disparate continents, we see a single, colossal landmass. This is Pangea. Imagine a supercontinent of truly unimaginable size spread across its expanses, sun-scorched deserts, ancient mountain ranges, full flowing rivers, and dense primeval forests. All of this was part of a single gigantic world. Titans of prehistory roamed this vast land, dinosaurs for whom the boundaries between what would become Africa and South America knew no bounds. A single, boundless ocean washed only the shores of this gigantic world island. But while life teemed on the surface of Pangea, deep within the planet's depths, hidden from view, forces capable of tearing this world apart were already awakening. What caused these lands to come together? What force then tore them apart? And what secrets does the Earth's crust still hold in the places where the ancient continents once converged? Get ready. We're heading into the very heart of prehistoric Earth. Imagine an era when the entire continent of our planet was gathered into a single, gigantic landmass, an incredible supercontinent stretching practically from one icy pole to the other. This colossal temperature difference made survival here a true test of endurance, and this shift from hell to glacier occurred almost daily. With the arrival of the different seasons, the contrasts became even more stark. Summers were unbearably hot, and winters were icy and harsh. The air here was thin, dry, and almost always filled with clouds of dust raised by the incessant winds. But Pangea's influence on climate didn't end there. The location of this supercontinent at the very center of the planet completely reshaped the weather patterns of the entire Earth. When the land was surrounded by a single global ocean, air and water circulation was radically different from today. During the hot summer months, the gigantic landmass heated up much faster than the ocean. This created a colossal low-pressure area that, like a powerful vacuum cleaner, sucked in moist air from the sea. This gave birth to super monsoons, incredibly powerful seasonal winds that make modern monsoons seem like a gentle breeze. Coastal areas likely experience torrential rains during these months, but these rains almost never reach the interior of Pangea. By the time the clouds reached the center of the continent, they had already given up all their water, leaving the inland desert dry and lifeless. As expected, in winter, the exact opposite occurred. The land cooled rapidly, forming high-pressure areas that forced icy, dry air outward toward the ocean. As a result, the continent became even more arid. It was the final act in the drama of Pangea's life, and simultaneously became the prologue to the history of the Atlantic Ocean, a history that is still being written right beneath our feet. It all began long before this mighty supercontinent began to break apart. Imagine the world of the Triassic period about 250 million years ago. At that time, the Earth's landmass looked and felt completely different. It was one gigantic landmass, stretching practically from pole to pole. This colossal chunk of the Earth's crust was pieced together like a gigantic mosaic. This land was not divided by oceans, as our modern continents. The climate on Pangea was harsh and sharply continental, especially in its vast interior. These areas would have resembled modern deserts with scorching summers and icy winters. The coastal regions, in turn, were somewhat milder and wetter. Because there were no vast oceans separating the land masses, animals and plants were free to roam across the continent. Species like early dinosaurs or small furry cynodonts, our distant ancestors, relatives of mammals, were free to roam these lands. There were no seas to act as barriers to their migration. This meant that life across Pangea was remarkably homogeneous. The planet was physically vast, but biologically it was closely interconnected. For animals and plants, Pangea was a single home, and the world seemed more compact than it is today. Differences between species in different regions were less noticeable. However, beneath this deceptively calm surface, deep within the earth, powerful processes were already gathering momentum. The rocky mantle beneath the crust was slowly shifting, driven by heat currents from the planet's scorching core. These movements had once assembled the gigantic continent of Pangea, but now they were also causing it to stretch, crack, and ultimately prepare it for its inevitable breakup. The supercontinent didn't split overnight as a result of some monumental cataclysm. No, it was an excruciatingly slow process, a titanic geological drama unfolding over tens of millions of years. Imagine, the first scars, harbingers of the Great Rift, began to appear on the body of the planet. These were gigantic faults in the crust, which we today call rift valleys. To understand what it was, look at the modern-day East African Rift Valley. Now magnify it tens, even hundreds of times. Then you'll get a sense of the scale of that prehistoric catastrophe. Within these gaping wounds, molten rock boiled, magma rising from the fiery depths of the planet. It erupted, flooding the surface with streams of boiling lava and creating vast fields of solidified dark volcanic rock. These colossal eruptions, known as trapped magmatism or flooded valleys, forever changed the face of the land and released so many gases into the atmosphere that they affected the climate of the entire Earth. Although these gigantic fissures weren't yet true oceans at the dawn of their existence, they were already becoming insurmountable physical barriers. New mountain ranges rose along the edges of the rifts, and their deep, scorching valleys made travel from one side to the other deadly for any living creature. Millions of years passed, and these rifts grew wider and deeper until finally their bottoms sank below sea level. This was a turning point. The waters of the great Panthalassa Ocean, which washed the single continent of Pangea, poured into these rifts. Gradually, new inland seas emerged in place of the dry land, narrow at first, but as impassable to land dwellers as the boundless ocean. Even if this new strait was only a few kilometers wide, for animals unable to fly or swim long distances, it was a veritable abyss. They found themselves trapped on their land masses, as if on giant islands. The wind could no longer easily carry plant seeds across these water barriers. Even winged creatures, birds, and insects found it increasingly difficult to navigate these new sea expanses. Thus began the great division of the world, and it was not only geographical, but also biological. This growing isolation triggered one of the most powerful drivers of evolution, so-called divergent evolution. Imagine a single large family of animals, separated by an insurmountable wall. Finding themselves in different environments and no longer able to interbreed, these two groups begin to evolve independently. Their genes no longer mix. They encounter different predators, different foods, and different climates. As a result, their bodies, habits, and lifestyles begin to diverge radically. As the continents, like giant ships, slowly drifted across the molten mantle, their fates diverged. Some approached the equator, transforming into hot and humid tropical paradises. Others, however, drifted toward the poles, where they became increasingly cold and arid. Each new continent acquired its own unique climate, flora and fauna, and, therefore, its own unique challenges for survival. This particularly profoundly transformed the plant world. During the time of a unified Pangea, vegetation was relatively uniform, but its split created a kaleidoscope of new climatic zones. In some places, rainfall increased, while in others, perpetual drought reigned. Even the composition of the soil changed. This led to a veritable explosion of diversity in the plant kingdom. Thousands of new species emerged, each perfectly adapted to its own small homeland. It was during this era that flowering plants, or angiosperms, entered the scene and began their triumphant march. They revolutionized life by inventing ingenious ways to attract pollinators, insects and birds, with vibrant petals and sweet nectar. They also developed new strategies for dispersing their seeds, perfectly suited to specific locations. Let's imagine an ancient fern that once grew across Pangea. When a new sea split its range in two, one population found itself on increasingly dry land and learned to survive in such soil. The other found itself in the tropics and adapted to rapid growth in evergreen forests. Over millions of years, these two ferns, despite descending from the same ancestor, became completely different species. But even more striking metamorphoses occurred among animals. Take, for example, the early mammals. During the time of Pangea, they were tiny, mostly nocturnal creatures hiding in the shadow of giant dinosaurs. But the breakup of the continents gave them the chance to follow different evolutionary paths. One of the most striking examples is the split between marsupials and placentals. Marsupials, like modern kangaroos, which give birth to tiny, underdeveloped young that are then carried in a special pouch on their abdomen, came to dominate the southern continents, the fragments of ancient Gondwana, the future Australia and South America. At the same time, placental mammals became dominant on the northern continents that made up Laurasia, the future North America, Europe, and Asia. They carried their young in the womb until they reached full maturity. Growing oceans became an insurmountable barrier between these two groups, and they evolved in complete isolation for tens of millions of years. It was this separation that gave rise to the incredible diversity of mammals we see today. Even dinosaurs, the undisputed rulers of the Mesozoic era, couldn't escape the consequences of this slow but inexorable disintegration of the world. During the Triassic and early Jurassic periods, dinosaur species across the planet were remarkably similar. But as the continents drifted apart and the oceans expanded, different dinosaur families became isolated and began to evolve in their own unique ways. Thus, gigantic, long-necked sauropods and armored stegosaurs gave rise to a multitude of new, bizarre forms. adapting to the unique conditions of their continents. On the southern continents, for example, a group of massive sauropods known as titanosaurs flourished particularly well. These living mountains took on a wide variety of shapes and sizes, evolving completely differently from their northern relatives. Separated by thousands of kilometers of ocean, each group developed its own survival strategies, shaped by a unique set of plants, predators, and climate. And this process affected more than just the famous giants. Small creatures, insects, amphibians, freshwater fish were also caught up in this great drama. Rivers that once flowed peacefully across Pangea were torn apart by new mountain ranges and oceans. The fish that inhabited these rivers found themselves trapped in new, isolated bodies of water and over time evolved into entirely new species. Amphibians, bound to humid environments, found themselves confronted with arid interiors of continents and impassable salty oceans. As a result, each continent developed its own unique species of frogs, salamanders, and newts. All these biological changes were inextricably linked to global climate change. As the continents shifted, the routes of ocean currents and prevailing winds shifted. The single ocean of Panthalassa gave way to a more complex system, with new Atlantic and Indian Oceans. This completely redrew the map of currents that transport warm and cold water across the planet, leading to the emergence of entirely new climate zones. Some regions became humid and covered in dense tropical forests. Others, by contrast, turned into lifeless deserts. Seasons became more pronounced and extreme. Animals and plants had no choice but to adapt to these new rules of the game. They had to learn to survive long droughts, endure cold winters, and sweltering summer heat. Volcanic activity accompanying the breakup of the continents released enormous quantities of greenhouse gases into the atmosphere, triggering periods of global warming. But then, ironically, the emerging new oceans began to absorb carbon dioxide from the atmosphere, which in turn led to periods of cooling. The planet breathed, changed, and life on it changed along with it. Imagine a geological mystery scattered across the globe. On one ocean shore, we find unique rock structures, and then thousands of kilometers away, on another continent, we discover their exact mirror image. These striking geological twins serve as irrefutable proof of the old, once ridiculed theory of continental drift. Look at the mountain ranges that today are separated by entire oceans. Their contours, curves, and gigantic cracks, so-called faults, align with astonishing precision. They are like scars on the planet left by a titanic collision. A picture of the distant past unfolds before us when these colossal land masses not only stood side by side, but smashed into each other with unimaginable force, crushing the rock into gigantic folds. Moreover, when scientists map the hotbeds of volcanic activity and earthquake epicenters on the world map, they see a striking pattern. These formidable and destructive phenomena do not occur chaotically. On the contrary, they line up in clear lines, outlining the boundaries of those very tectonic plates. This is exactly the picture we would expect to see if the Earth's crust consisted of giant moving blocks, constantly colliding and rubbing against one another. Even the silent ocean floor holds a piece of this grand history. Thanks to deep-sea drilling technology, researchers have been able to recover rock samples from the ocean floor. Analysis of these cores has allowed researchers to determine the age of the seafloor with incredible precision and understand how it was formed and grew. This knowledge fits perfectly with the theory of plate tectonics, confirming its boldest predictions. These days, geologists peer deep into the planet's interior using a technique called seismic tomography. This approach tracks how seismic waves from earthquakes travel through the Earth, creating a kind of giant X-ray of our world. These 3D images reveal a stunning picture. Gigantic columns of hot rock, known as mantle plumes, rise from the deepest depths, while cooler, heavier layers of rock sink downward, like logs in a giant fireplace. These processes vividly demonstrate how the interior of our planet is constantly shifting and churning. This process, known as mantle convection, is the engine, the hidden force that drives the continents on the planet's surface on their slow but inexorable journey. This incredible scientific journey began with Alfred Wegener's bold, once ridiculed hypothesis of continental drift. But by the mid-20th century, the modern theory of plate tectonics had become one of the greatest achievements in the history of science. It was a triumph of evidence-based thinking, demonstrating how irrefutable facts can crush any doubts and objections. This perpetual cycle of air masses, generated by Pangea's enormous size and unique shape, created global weather systems that were chaotic and incredibly intense. It's hard to even imagine how alien and extreme the weather on our planet was in those distant times. The interior of Pangea wasn't just a dry place, it was a land of absolute extremes, with deadly heat and bitter cold, endless deserts and towering mountains, perpetual dust storms, and long-forgotten inland seas. And only thanks to the rocks and fossils this era left behind, do we now know that this ancient supercontinent had a colossal impact on Earth's climate, leaving a profound mark on our planet's history. The history of our world is full of fascinating chapters. Pangea, this ancient Earth, was not only a realm of towering mountain ranges, but also a vast and diverse landscape. It was a veritable patchwork of wide open plains, majestic plateaus, deep valleys, and constantly shifting basins. The mountain belt, the ancestor of today's Appalachians, proudly cut through the northern and central parts of the supercontinent, creating a multitude of truly spectacular landscapes. However, it wasn't only mountains that shaped the face of Pangea. Between them stretched vast flat plains and low-lying basins. Some were dry and dusty, while others could become shallow seas or temporary lakes, especially during warm periods when global temperatures rose and the hydrological cycle became more active. This story serves as a timeless reminder of the importance of approaching any problem from multiple perspectives, bringing together geologists, physicists, chemists, and even space technology specialists. Today, plate tectonics is the foundation upon which our understanding of the ever-changing face of our planet is built. This theory not only explains the past of the Earth's continents, but also allows us to peer into their distant future. After all, it was this global mechanism that, more than 300 million years ago, brought together the ancient supercontinent Pangea, and then mercilessly split it into pieces, giving birth to modern continents and oceans, and predetermining the paths of evolution and the dispersal of life across the Earth. When we delve into our planet's deep past, into times difficult to even imagine, one name invariably comes to mind: Pangea, This colossal landmass is undoubtedly the most famous of all the supercontinents. It was the last time virtually all of Earth's land was united into a single monolith. Its subsequent breakup was the event that created the modern world map we've known since school. But to truly grasp the grandeur and significance of Pangea, we must journey even further back in time, long before its parts came together. The fact is, Pangea wasn't the only supercontinent to ever exist on Earth, and it certainly wasn't the last. In fact, our planet has experienced numerous great cycles, during which its continents slowly converged to form a single, gigantic landmass, only to break apart again millions and millions of years later. This endless process of assembly and disassembly is known as the supercontinent cycle. It's driven by the slow but powerful flow of molten rock deep beneath the Earth's crust, in the mantle. This powerful cycle of supercontinent formation and disintegration has been ongoing for billions of years. Each cycle leaves its imprint on the rocks, mountains, and magnetic anomalies of the Earth's crust, evidence that scientists carefully collect and analyze to unravel the mysteries of the planet's inner workings and reconstruct its long, dramatic history. By studying the supercontinents that predated Pangea, such as Kenorland, Columbia, sometimes called Nuna, and Rodinia, paleogeologists have been able to reconstruct an incredible record of Earth's evolution. They have seen how the planet's appearance changed and how life itself adapted to these monumental shifts. Let's return to those immemorial eras when life on Earth was just taking its first steps and the air we breathe didn't even exist. Our journey begins in the time known as the Neo-Archean era, which spanned approximately 2.7 to 2.5 billion years ago. It was during this period that the supercontinent Kenorland likely formed, one of the oldest giant continents, whose existence is now supported by compelling geological evidence. Try to imagine this alien, almost extraterrestrial world. Perhaps the sun didn't shine as brightly back then as it does today. The atmosphere was practically devoid of oxygen, and life, if it existed, was limited to the simplest microscopic organisms. But deep beneath the surface, the same titanic forces that still drive the movement of continents today were already at work. Kenorland wasn't composed of the continents we know today. It was cobbled together from numerous smaller land masses called proto-continents and ancient, incredibly strong rock blocks that scientists call cratons. These cratons are the oldest and most stable parts of today's continents. Among the ancient blocks that once made up Kenorland were the Baltic Shield, now part of Scandinavia and Eastern Europe, the Superior Craton in North America, and the Ilgarn Craton in Western Australia. Scientists didn't find a single gigantic landmass called Kenorland. Instead, they inferred its existence by comparing very ancient rocks from different continents and discovering that they once fit together perfectly. They used paleomagnetic data, a kind of ancient magnetic compass frozen in rock, to prove that these now distant lands were once connected. They also studied the age of the rocks, the location of ancient mountain belts, and found identical mineral deposits on different cratons. The emergence of Kenorland marked a turning point in Earth's history. The formation of this supercontinent marked a new era. It also helped us understand that colossal volcanic events can play a decisive role in continental breakup, a phenomenon we will also observe in the breakup of later supercontinents. Now let's fast forward to the Paleo-Proterozoic era, which lasted approximately 1.8 to 1.5 billion years ago. After Land broke apart, its debris didn't simply drift aimlessly through the world's oceans. For over 100 million years, it slowly but surely converged on one another, eventually forming a new, even grander supercontinent known as Columbia, also sometimes called Nuna. Columbia was significantly larger and geologically more stable than its predecessor. The process of its assembly was far more complex. It began with the collision of numerous ancient cratons and newly formed land masses. Try to imagine this scene: gigantic land masses, comparable in size to modern continents, slowly but inexorably smashing into each other. The force of these collisions was such that it gave rise to enormous mountain ranges, some of which may have towered over anything we see on Earth today. The key parts of Columbia were Laurentia, which later became the core of North America, and Baltica, part of what would become Scandinavia. Imagine a world where the contours of the continents, as we know them from maps, meant nothing. Let's travel back to the distant past, when disparate chunks of the Earth's crust, future Scandinavia, Eastern Europe, vast expanses of Siberia and northern China, as well as fragments of West Africa and even distant Australia, were drifting toward one another. Evidence for the existence of this ancient giant, which scientists have named Columbia, has proven far more compelling than that of its predecessors. Geologists, like detectives tracking an ancient event, have discovered gigantic scars on the planet's body, wide belts of ancient mountains. These so-called orogenic belts are essentially welds formed where these titanic plates collided. One of the most striking examples is the Trans-Hudson Orogen, a colossal region of folded and deformed rock that stretches across central Canada and the northern United States. In these zones of ancient cataclysms, scientists have also stumbled upon traces of anerogenic magmatism, mysterious volcanic activity that occurred without the formation of mountains, often during periods of calm, after the continents had become one. However, nothing lasts forever, not even supercontinents. Columbia was no exception. Its gigantic body began to crack at the seams approximately 1.5 billion years ago. Like other similar megastructures, it likely slowly broke apart through a process geologists call rifting. Imagine giant cracks and fissures forming in the Earth's crust, which over time turn into new ocean basins. The story of Columbia is more than just a chapter in a geology textbook. It has colossal significance for our understanding of how the entire tectonic system of the Earth worked and evolved. It clearly demonstrates how plate tectonics gradually gained momentum, becoming increasingly similar to the processes that shape our planet today. The formation and subsequent breakup of Columbia had consequences that went far beyond the simple movement of rocks and mountains. The Great Oxidation Event, the moment when our planet's atmosphere began to fill with life-giving oxygen, occurred even before Columbia came together. However, the subsequent fate of this supercontinent likely played a key role in the redistribution of nutrients in the world's oceans. This, in turn, may have spurred the development of early yet complex life forms, prokaryotes, that began to actively colonize the ancient world. Interestingly, paleontologists often refer to the period of Columbia's unified existence as the Boring Billion. This is an era when, at first glance, nothing truly exciting happened in the evolution of life. But this long period of tectonic calm actually demonstrates how the stability of a giant continent can directly influence the pace of evolution itself. Now, our journey into Earth's deep past takes us to the next era, the one that preceded the age of dinosaurs. We're heading to the Neoproterozoic era, which spanned from 1 billion to approximately 750 million years ago. It was then that another majestic supercontinent emerged on the planet, known to us as Rodinia. If Pangea is the true superstar among the ancient continents known by almost everyone, then Rodinia is its mysterious and perhaps far more powerful older brother. Although less famous, its history is no less, if not more, dramatic. After all, it was when Rodinia broke apart that Earth experienced some of the most extreme climate catastrophes in its entire history. Among them was a period when our entire planet was likely frozen solid from pole to pole, an event scientists call the snowball Earth hypothesis. And almost immediately after this icy apocalypse, the first truly large and complex life forms emerged. The very name Rodinia comes from the word meaning homeland, and it was truly a vast ancestral home for all life. Geologists calculate that it was most likely clustered around what we now call Laurentia, the ancient geological core that hundreds of millions of years later would become North America. However, Rodinia didn't form overnight. Its formation spanned millions of years and was associated with a massive mountain-building process known as the Grenville orogeny. This global tectonic cataclysm unfolded between 1.3 billion and 1 billion years ago. During this era, several ancient landmasses, including parts of what would become South America, Africa, Australia, India, and even Antarctica, slowly drifted toward one another. Eventually, they collided, pressing tightly against Laurentia. These titanic collisions crumpled the Earth's crust like a sheet of paper, lifting the highest mountain ranges to the heavens. Those mountains are long gone, ground to dust by time, but their deep rocky roots can still be found on various continents. And this is the best proof that all these lands were once a single entity, Rodinia. But how can we be so sure that Rodinia truly existed? Geologists have assembled a mosaic of evidence from across the globe. Paleomagnetic data, a kind of compass embedded in ancient rocks, helps determine where on the planet the rock was when it formed. The striking similarities in rock types and geological structures across continents today, separated by thousands of kilometers of ocean, provide another compelling argument. For example, rocks from the Grenville Fold period found in eastern North America bear an incredible resemblance to rocks from as far away as Scandinavia, the British Isles, and even Antarctica. All this evidence, like threads, leads to one conclusion. These lands were once inextricably linked as part of the gigantic continent of Rodinia. However, the history of Rodinia is not limited to its monumental formation. Its breakup, which began around 750 million years ago and continued for the next 200 million years, was an event no less significant and far more turbulent. Scientists theorize that gigantic columns of superheated rock, so-called mantle plumes, may have formed deep beneath Rodinia. Like a giant gas burner, they began to burn through the continent from within, splitting it apart. This process created new coastlines and vast, shallow seas. The newly exposed land masses began to undergo intense weathering, which, like a sponge, rapidly absorbed carbon dioxide from the atmosphere, the planet's main blanket, responsible for the greenhouse effect. As a result of this chemical weathering, its concentration in the air plummeted, and without sufficient carbon dioxide to trap heat, Earth's climate began to rapidly cool. The volcanic activity that accompanied the continental breakup may have temporarily warmed the planet, but it was far from sufficient to prevent a global freeze. Ultimately, ice likely covered virtually the entire surface of the Earth, from the oceans to the equator. But, as often happens in the history of our planet, this icy catastrophe served as the impetus for new beginnings. Scientists believe that the colossal environmental stress experienced by Earth during those frigid times literally forced life to evolve, seeking new, more complex paths of development. Indeed, shortly after the end of the Ice Age, the first large multicellular organisms, known as the Ediacaran biota, appeared in the oceans. These vast basins, depending on their elevation and proximity to moisture sources, could dramatically change their appearance from season to season or across geological epochs. Over millions of years, these depressions would fill with water during rainier periods, turning into inland seas or vast salt lakes. However, for most of that time, they remained dry, sun-baked lands, where sand, driven by hurricane winds, accumulated in thick layers. Over time, as the water evaporated, thick salt crusts formed here, a silent testimony to ancient arid conditions. With the onset of the Permian period, which lasted from approximately 299 to 252 million years ago, Pangea began to experience the first signs of lethal stress, the processes that would much later lead to its breakup. The Earth's crust began to slowly stretch and thin in some places, revealing the very first scars on the supercontinent's body. These early faults formed long, low depressions in which water sometimes accumulated, forming narrow lakes or seasonal rivers. Where the cracks ran deep enough, volcanic activity could also awaken. Magma erupted to the surface, especially within the massive continent. However, most of the large volcanoes remained on the margins of Pangea, near zones where oceanic crust was subducting beneath continental crust, a process known in geology as subduction. Pangea's fluvial arteries were truly impressive. This incredible evolutionary leap laid the foundation for the subsequent Cambrian explosion, which ushered in staggering biodiversity. Thus, Rodinia didn't just change Earth's geography, it influenced the very course of life. However, it was not alone in shaping the history of our planet. It was preceded by at least two earlier supercontinents, Columbia and the even more ancient Knorrland. All of these stages are just parts of a much larger story known as the supercontinent cycle. The essence of this idea is astonishing. Continents never stand still. They slowly coalesce, forming vast land masses and then break apart again, obeying a repeating cosmic rhythm. Each such cycle lasts from 300 to 500 million years. These are truly gigantic periods of time, difficult to even imagine, yet they are an integral part of the structure of our planet. There are two main theories about how supercontinents form. One is the introversion model. According to it, a new supercontinent forms in the place of the old one, closing the internal oceans left behind by its breakup. The other model, the extroversion model, describes how fragments of the old continent drift across the planet and meet on the opposite side of the globe, closing the outer global ocean in the process. But regardless of the specific scenario, the basic process remains the same. The land masses converge, mantle heat accumulates beneath them like a giant blanket, and this heat eventually tears the continent apart. The fragments then drift apart for hundreds of millions of years until they collide again, beginning a new cycle. This great cycle has a profound impact not only on geography, but also on Earth's climate, sea levels, ocean currents, and even the evolution of life itself. When all the continents merge into one, the interior of this gigantic land mass often becomes arid, parched deserts, as it is too far from the life-giving moisture of the oceans. Ocean currents, these global heat transport belts, are blocked or reversed, causing warm water to be distributed across the planet in a completely different way. All of this can lead to dramatic climate change. Even albedo, a measure of how well a planet's surface reflects or absorbs sunlight, changes depending on the amount of ice and land. The supercontinent cycle also directly influences the global carbon cycle. When supercontinents break apart, volcanic activity increases sharply, releasing massive amounts of carbon dioxide into the atmosphere and likely warming the planet. However, new young land masses are subject to intense weathering, which draws carbon dioxide back from the atmosphere, leading to cooling, exactly as happened during the snowball Earth. Sea levels rise as continents move apart due to the growth of underwater mid-ocean ridges, which literally displace water. And when the continents reappear, their movement slows and sea levels begin to fall. Even the evolution of life itself follows the rhythm of this great cycle. When continents collide or drift apart, they create entirely new conditions that favor the emergence of some species and the extinction of others. The creation of new ecological niches and the destruction of old ones is a natural process that can lead to both mass extinctions and explosive bursts of evolution. New shallow seas that formed in rift zones became ideal incubators for thriving marine life. And as we have already seen with the breakup of Rodinia, this cycle also helps explain why we find valuable mineral resources in specific locations today. Many of the world's most important ore deposits were formed either by the collision of continents under enormous pressure or by the upwelling of magma during their breakup. On Earth's grand timeline, each of these ancient supercontinents opened a new chapter in the history of life. We have already witnessed the formation of our planet's crust, its cooling, and its stabilization. We've seen geological processes gaining power, becoming increasingly complex and large-scale, laying the foundation for the plate tectonics we know today. We've even peered into the depths of time and seen how the Earth's titanic forces are capable of not just reshaping landscapes, but also guiding the very course of evolution. But none of these stories compares in scope to the saga of Pangea, the gigantic supercontinent that once united almost all of our planet's landmass. It's more than just a tale of shifting rock and tectonic plates. It's an epic tale woven into the very fabric of life on Earth. The birth of Pangea was not a single event. Imagine a leisurely, grand journey spanning hundreds of millions of years. To witness the birth of this giant, we must travel back in time to the era known as the Paleozoic era. This incredible span of time began approximately 541 million years ago and ended approximately 252 million years ago. Paleontologists rightly call it the age of ancient life. It was then that a veritable evolutionary turmoil unfolded on the planet as life continually took on new forms. In those distant times, Earth was a world in flux. The climate shifted with kaleidoscopic speed, and the continents never stood still. They were eternal wanderers, drifting across the molten mantle, colliding with one another, and redrawing the map of the planet. It was a titanic ballet in which disparate land masses, as if in slow motion, slowly converged. And finally, after millions of years of this cosmic dance, they converged in a mighty collision, giving birth to a single continent, Pangea. During this time, life itself made incredible leaps. It evolved from primitive marine organisms to the most complex plants and animals that dared to venture onto land for the first time. The first dense forests spread across the planet, strange creatures flourished in the oceans, and on land, reptiles took their first steps toward their future dominance. And all the while, the continents, like giant pieces of a cosmic puzzle, moved inexorably toward one another. At the beginning of the Paleozoic, the Earth's appearance bore no resemblance to its present-day form. The continents were fragmented into countless pieces. These were the remains of an even older supercontinent, Rodinia, which had already broken apart. But amid this chaos, two future giants were already emerging, two enormous land masses destined to play a key role in the coming planetary drama. Their names were Gondwana and Laurasia. A true colossus reigned supreme in the south of the planet, the supercontinent Gondwana. It's important to understand that it didn't just emerge out of nowhere in the Paleozoic. It already existed, assembled from fragments of a previous world left behind by the breakup of Rodinia. Gondwana was colossal, and for most of the Paleozoic era, it remained the largest landmass on Earth. Imagine its scale. It included lands that, eons later, would become the familiar South America, Africa, Antarctica, Australia, Hindustan, Madagascar, the Arabian Peninsula, and even small fragments of today's Florida and southern China. At the dawn of the Paleozoic, approximately 541 million years ago, this giant was located primarily in the southern hemisphere, with a significant portion of it located near the South Pole. Like a gigantic ship, Gondwana began its slow but inexorable northward drift, covering thousands of kilometers across the face of the planet. This great journey inevitably brought about dramatic changes. As Gondwana moved, its various parts found themselves in completely different climate zones. During the Ordovician and then Carboniferous periods, vast tracts of Gondwana were submerged in glacial periods, covered by kilometers-thick ice caps. And evidence of this journey is carved in stone. In the rocks of modern-day India and Africa, where unbearable heat reigns today, paleontologists are finding deep scars left by ancient glaciers, so-called glacial grooves. These icy imprints are irrefutable evidence that these lands once stood at the very celestial pole. As the continent shifted toward warmer latitudes, its interior turned into arid, parched deserts. However, The coasts and regions with milder climates were true oases, home to the richest ecosystems. One of the jewels of Gondwana was the vast tropical forest, stretching across vast territories. And the best evidence of this unified world is found in the plant world. A special species of fern, known as Glossopteris, was incredibly widespread across Gondwana. Its fossils are found today on all the continents that were once part of this supercontinent, providing direct evidence of their former unity. Gondwana influenced more than just life. Its enormous size altered ocean currents and global winds, shaping the entire planet's climate and determining where torrential rains would fall and which lands would turn into deserts. Meanwhile, in the northern hemisphere, the picture was completely different. Instead of a single monolith, a veritable archipelago of continental plates sprawled here. Among them were such large land masses as Laurentia, which would later form North America, as well as Greenland, Baltica, the future Scandinavia and part of Eastern Europe, Siberia, and Avalonia, which included parts of Western Europe, including Great Britain and Ireland. These northern lands were scattered, each moving along its own trajectory. Unlike Gondwana, which was a single entity, they were in constant motion and interaction. Only over time did these northern territories slowly begin to converge, eventually merging into a new supercontinent, Laurasia. This process, accompanied by violent geological cataclysms and collisions, forever changed the face of the northern hemisphere. These isolated continents developed their own unique plant and animal forms, very different from those of Gondwana. These biological differences vividly demonstrate how distinct these worlds were until Pangea was finally born, allowing species from the north and south to mingle in a single melting pot. The entire Paleozoic era can be imagined as a gigantic film shot in slow motion. In it, the continents perform their slow but majestic dance, inexorably moving toward a grand finale. And that finale was truly spectacular. The formation of Pangea was not the result of a single impact. It was the culmination of a series of devastating collisions. The first act of this drama was an event geologists call the Caledonian orogeny. It unfolded during the Silurian and Devonian periods, approximately 440 to 390 million years ago. It was the gradual merging of three northern continents, Laurentia, Baltica, and Avalonia. The ancient Iapetus Ocean separating them began to tighten like a giant vice as the continents inexorably converged. And when these land masses finally collided, the force of the impact was such that the Earth's crust crumpled like paper. New, young mountain ranges rose skyward. Even today, after hundreds of millions of years of erosion, we see their time-worn remains in the Appalachian Mountains of eastern North America, the Scottish Highlands, the Scandinavian Mountains, and the coast of Greenland. This monumental merger resulted in the birth of a new northern supercontinent, often referred to as Euramerica or Laurasia. The key moment in this process was the so-called Akkadian orogeny in the Devonian period, when Avalonia slammed into the already merged continents, creating even more mountains and finally cementing the northern lands into a single monolith. And now the moment has arrived for the grand finale. The greatest collision in the history of our planet occurred during the Carboniferous and Permian periods, approximately 320 to 250 million years ago. It was the moment of truth, when the two giants Gondwana, and Laurasia finally met in a final decisive clash on a planetary scale. Two key events mark this period: the Alleghenian orogeny and the Variscan orogeny, also known as the Hercynian. The Alleghenian orogeny resulted from the collision between Africa, part of Gondwana, and the east coast of North America, part of Laurasia. This powerful impact finally shaped the Appalachian Mountains, transforming them into a rugged and towering range. At the same time, at the other end of the converging worlds, the equally grandiose drama of the Variscan orogeny was unfolding. Africa and smaller continental fragments slammed into Europe, causing colossal tectonic shifts. These processes gave rise to mountain ranges that stretched across Central and Southern Europe. These were the early ancestors of today's Alps, Pyrenees, and Ural Mountains. But these titanic collisions didn't just create mountains. They deformed the Earth's crust, triggered unprecedented volcanic activity, and altered the planet's very chemistry. Layer by layer, impact after impact, the geological puzzle came together. And finally, the picture was complete. All the planet's major land masses merged, creating a single colossal supercontinent known as Pangea. Pangea stretched from the North Pole to the South Pole and was surrounded by a single global ocean, which paleontologists call Panthalassa. For hundreds of millions of years, the continents slowly drifted toward this point. And during this same time, life on our planet experienced the most dramatic and breathtaking transformations in its history. Earth was not always as we know it. In its vast history, there exists a monumental chapter known to science as the Paleozoic Era. Imagine a time span that stretched an incredible 300 million years, from 541 to 252 million years before the present day. It was an era of colossal change, when the planet itself was changing its appearance, and life, originating in the ocean, waged a desperate struggle for existence, colonizing new worlds and experiencing the most devastating extinctions of all time. Let's travel back to the very beginning of this era, to the Cambrian period, which began approximately 541 million years ago. It was then, in the primeval seas, that something incredible happened, an event paleontologists call the Cambrian explosion. It was a true biological Big Bang. In a seemingly insignificant amount of time in geological terms, a staggering diversity of life emerged from the ocean depths. Nearly all the fundamental animal phyla that exist today, from the ancestors of vertebrates to arthropods, suddenly appear in the fossil record. Due to the continent's colossal size, stretching nearly from pole to pole, it required gigantic rivers to transport water across its surface. But many of these rivers met a tragic fate. They never reached the ocean. Instead, they flowed into the arid heart of the continent and emptied into inland basins, where their water simply evaporated under the scorching sun, leaving behind only flat, dry lake basins or sparkling salt marshes. The few rivers that did manage to reach the great ocean of Panthalassa were true giants, monsters of the water world. They drained vast territories, transporting water over incredible distances. Unlike today's world, where there are numerous small continents surrounded by oceans, Pangea had only a few places where rainwater could find its way to the sea. This is what made Pangea's climate system so unique. Even the chemical composition of the oceans was altered by weathering and erosion processes occurring deep within the continent. When we look at Pangea's climate during the Permian, we see a world that was both bizarre and extreme. Atmospheric carbon dioxide levels were significantly higher than today, contributing to overall planetary warming. However, this heat was distributed extremely unevenly. Due to its vast surface area, Pangea had what scientists call thermal inertia. It warmed and cooled very slowly. This explosive flowering of life had not yet touched land, which remained a lifeless desert. All the action unfolded in the warm, shallow seas that stretched along the edges of the newly formed continents. The breakup of the giant supercontinent Rodinia created ideal conditions, endless shelves, sunlit and rich in nutrients. These were the perfect cradles for life to thrive. Then came the next era, the Ordovician period, which lasted from approximately 485 to 443 million years ago. Life in the oceans continued to evolve, becoming increasingly complex and sophisticated. It was during this time that the first true vertebrates, our most distant ancestors including primitive forms of fish, emerged. But the most astonishing event unfolded on the deserted continents. Plants, those humble pioneers, began their great march onto land. Of course, these were not yet mighty forests, but simple, avascular organisms. But their appearance marked a turning point in the planet's history. However, the end of this period was written not in ink, but in ice and death. The planet faced one of its first global catastrophes, a mass extinction. Scientists believe that the drift of the enormous southern continent of Gondwana, which slowly but inexorably slid toward the South Pole, was to blame. This movement set the wheels of the Ice Age in motion. The polar ice caps began to expand, trapping water, sea levels dropped catastrophically, and countless marine species, unable to adapt, disappeared forever from the face of the earth. When the ice retreated, the Silurian period began, lasting from 443 to 409 million years ago. The seas were once again teeming with life, and evolution took a crucial step forward. Fish with jaws appeared. This was a revolutionary innovation, a true weapon in the struggle for survival. Meanwhile, on land, plants continued their expansion. They developed a vascular system, a kind of internal plumbing for transporting water and nutrients, allowing them to break through. And they were no longer alone. Following them, the first animal colonizers crawled onto the moist land. Tiny creatures, similar to modern centipedes and scorpions, became the first timid inhabitants of land. And beneath their feet, the continents continued their perpetual motion, shifting ocean currents and creating new arenas for the great drama of evolution. The next chapter is the Devonian period, from 419 to 359 million years ago. It's often called the Age of Fishes, and for good reason. The oceans of that time were teeming with a wide variety of fish species. Some were encased in bony armor like living tanks. Others developed powerful jaws, and still others even learned to breathe atmospheric air. But the most monumental achievement of this time occurred at the boundary between land and water. The first amphibians emerged from the water, vertebrates that took a decisive step in the exploration of a new world. This was the prologue to the conquest of the continents. Simultaneously, the land itself was being transformed. The first true forests in history, composed of gigantic tree-like plants, began to emerge. These primeval jungles forever changed the face of the planet, anchoring the soil with their roots, saturating the atmosphere with oxygen, and laying the foundation for all future terrestrial ecosystems. The slow but relentless movement of tectonic plates only accelerated these changes, reshaping coastlines and altering the climate. Next comes the Carboniferous period, which lasted from 359 to 299 million years ago. Imagine a world covered in endless, steamy, swampy forests. These were especially dense on the continent of Laurasia. These forests were so colossal that when trees died, their trunks fell into the viscous bog where, over time, under the pressure of the Earth's interior, they turned into the very coal that humanity uses to this day. Amphibians thrived in these swamps, but new players also entered the scene, the first reptiles. These creatures possessed a revolutionary advantage. They learned to lay eggs directly on land, allowing them to break away from bodies of water and move deeper into the continents. This was a crucial evolutionary leap. At the same time, two ancient continents, Laurentia and Baltica, collided in a titanic, slow-motion battle, forming a new northern supercontinent, Euramerica. This geological cataclysm altered the climate, creating the very humid and oxygen-rich environment in which life thrived. Oxygen concentrations in the atmosphere reached historic highs, allowing some insects, such as dragonflies, to grow to monstrous sizes with wingspans of almost a meter. And so we come to the Permian period, the final act of the Paleozoic era, which lasted from 299 to 252 million years ago. This era was simultaneously a time of life's greatest triumph and its most terrible tragedy. By this point, almost all of the planet's land had merged into a single gigantic supercontinent, which scientists have named Pangea. Reptiles, as the true masters of the land, spread across these vast expanses, adapting to a wide variety of conditions. However, this unification had a downside. The interior of Pangea turned into parched, arid deserts. The global system of ocean currents shifted, new mountain ranges emerged, and the climate became extremely unstable and unpredictable. The planet was bracing for catastrophe. These changes created all the conditions for the largest mass extinction in Earth's history, known as the Great Dying. It was an apocalypse that wiped out up to 90% of all marine species and 70% of terrestrial vertebrates. One leading theory holds that the trigger was the monstrous volcanic eruptions in what is now Siberia, the so-called Siberian traps. For millions of years, the Earth spewed lava flows, releasing unimaginable amounts of greenhouse gases into the atmosphere. This triggered rapid global warming, turning the oceans into acidic cauldrons and collapsing ecosystems across the planet. Some researchers also believe that the very formation of the gigantic Pangea may have disrupted the planet's internal thermal dynamics, only exacerbating this global agony. Throughout the Paleozoic era, our planet was in constant flux, both literally and figuratively. The climate fluctuated constantly from stifling heat to icy cold, especially during the Ordovician and Carboniferous periods, when gigantic glaciers formed at the poles. Plants, especially during the Carboniferous, rapidly advanced on land. They acted as a gigantic factory, saturating the atmosphere with oxygen. This oxygen not only supported new life forms, but also allowed some creatures to reach truly gigantic sizes. Continents slowly drifted, seas advanced and retreated, mixing nutrients and creating ever-new conditions for evolutionary experimentation. But the Paleozoic era was more than just a prologue to the age of dinosaurs. It was a time of incredible, dramatic transformations. Over hundreds of millions of years, life made its boldest strides, from microscopic organisms in the ocean to conquerors of land and builders of gigantic forests. Beneath the feet of these creatures, the Earth's crust slowly shifted, like gigantic ice flows driven by powerful currents deep within the mantle. The ancient continents of Gondwana and Laurasia, like two titans in slow motion, inexorably converged. Their collision, which ultimately gave birth to the supercontinent Pangea, forever changed the face of our world. Imagine that the Earth's surface is not a monolithic solid shell, but a gigantic living mosaic, and each fragment of this mosaic is in perpetual incessant motion, slowly, imperceptibly to the eye, but with inexorable force. This idea underlies the theory of plate tectonics, a concept that has revolutionized our understanding of the planet. The Earth's outer layer, the lithosphere, is broken into several colossal plates. These plates literally float on a more viscous plastic layer beneath them, the mantle. And although the speed of their movement is negligible, just a few centimeters per year, it is this patient, relentless sliding that creates the most magnificent landscapes on our planet. Moving plates can move apart, creating new oceans. They can slide past each other, causing earthquakes. But the most spectacular spectacle occurs where they collide, especially when two massive continental plates collide. This isn't just any collision. We're talking about processes that have shaped the planet over tens of millions of years. These geological titans are responsible for the birth of Earth's highest mountain ranges, leaving gigantic scars on its surface that tell us the stories of ancient supercontinents like Pangea. When two continents collide, it's a complex process. Try submerging two large corks in a bucket of water. Both will resist. Both will try to stay afloat. So it is with continental crust. It's thick and relatively light, reluctant to sink into the dense mantle. Instead of one plate submerging the other, the rocks caught between these two hammers begin to crumple, bend, and break. They rise up, forming the highest mountains. It's like pushing a carpet from two opposite sides. It will inevitably wrinkle. Imagine titanic forces crumpling the Earth's crust like a giant sheet of paper. Geologists call this monumental process orogeny, or more simply, the birth of mountains. But mountains are more than just a pile of rocks on the surface. Beneath them lies a profound foundation of thickened crust, extending into the Earth's depths like the keel of a mighty ship or the root of a colossal tree. This powerful anchor prevents the mountains from collapsing under their own weight and participates in a complex process of equilibrium that scientists call isostasy. It involves mountains slowly rising or sinking like a giant iceberg in the planet's mantle in response to changes in their own weight. For example, when relentless erosion wears away their peaks, or when billions of tons of glaciers melt and disappear. One of the most striking examples of mountain systems born in the throes of the formation of the supercontinent Pangea is the Appalachian Mountains, which stretch along the east coast of North America. Today's Appalachians are a mere shadow of their former grandeur, gentle, forested hills dwarfed by the jagged, icy peaks of the Himalayas. But don't let their modest appearance deceive you. Let's fast forward hundreds of millions of years into the past. Here, on this very spot, a colossal mountain range towered toward the heavens, its peaks rivaling those of today's Himalayas. The birth of the Appalachians was not a single event. It was a saga spanning hundreds of millions of years, a series of crushing collisions of continental plates. The final and most powerful chord of this drama was the Allegheny orogeny, which unfolded between 320 and 280 million years ago. At that moment, North America's ancient ancestor, known to geologists as Laurentia, collided with Gondwana, the gigantic southern supercontinent. The part of Gondwana we know today as Africa slammed into Laurentia with inexorable force. But even before this titanic collision, the region was already geologically active. Earlier cataclysms, such as the Taconian and Akkadian orogenies, had already set the stage. These ancient processes were associated with the slow closure of the ancient Iapetus Ocean, as volcanic island arcs and small microcontinents collided with Laurentia one after another, welding themselves to its edge. These early collisions laid the foundation for future events. However, it was the Allegheny collision that proved the final, decisive blow, giving this region its final form. During this epic battle of the continents, existing rock layers accumulated over millions of years were crushed into monstrous folds, fractured, and pushed westward. Gigantic sheets of rock, tens of kilometers thick, slid over each other, covering hundreds of miles and forming what we today call Africa. Some layers of the Earth's crust literally slipped over others, creating what geologists call a belt of folds and thrusts. It was this phenomenon that gave rise to the mighty Appalachian Mountains. There is even a visible boundary to this deformation, known as the Allegheny Front, the boundary beyond which the Earth's crust underwent its most radical changes. The scale of this phenomenon, this birth of mountains, is staggering. Experts believe the ancient Appalachians could have reached heights of 8 or even 9,000 meters. A world of icy peaks, thin air, and perpetual winds, comparable to the highest points on our planet today. This mountain range stretched for thousands of kilometers, serving as the central spine of the newborn supercontinent Pangea. And although over the past hundreds of millions of years, wind, water, and ice have done their work, wearing these majestic peaks down to their very foundations, their ghosts still live on. The parallel ridges and deep valleys of the central and southern Appalachians are nothing more than traces of those gigantic folds and faults. And if we peer into the very heart of the mountains, we find metamorphic rocks, schist and gneiss, rocks that were literally baked and compressed by the hellish heat and pressure of mountain building. Vast masses of eroded rock, sandstone, shales, and conglomerates were eroded from these mountains and deposited in adjacent basins to the west, forming what geologists call Piedmont basins. These thick layers of sedimentary rock are all that remain of what were once the greatest mountains on the planet. Now, looking at this landscape, we see not just hills, but an entire chronicle stretching back centuries. Now let's cross the Atlantic Ocean and look at Russia. Here we see another mountain range with a strikingly similar fate, the Ural Mountains. These rugged, majestic peaks, rising to heights of over 1,500 meters, stretch from the Arctic Ocean in the north to the Ural River in the south. This meant that there were vast temperature differences between the scorching equator and the cold poles, and the seasons were very sharp and intense. Even though the poles were part of a single land mass, they likely still experienced long, freezing winters, perhaps even with the formation of large seasonal glaciers. However, compared to earlier periods such as the Carboniferous, when Earth was locked in extensive glaciation, the Permian epoch was largely ice-free. Rocks and fossils found on modern continents reveal this ancient climate. For example, coal seams, which form in warm, swampy environments, are found only in thin bands along the edges of what was once Pangea. This is direct evidence that much of the interior was too dry to support dense forests or marsh plants. On the other hand, in the central and subtropical regions of the former Pangea, we find numerous layers of red rock and salt deposits, a sure sign of widespread deserts. The climate of Pangea was a world of stark contrasts. In the very depths of the supercontinent, far from the moderating influence of the ocean, vast deserts lay where mighty winds reigned supreme. Let's travel back in time, hundreds of millions of years ago, to a time when lifeless land stretched beyond the colossal mountain ranges. The supercontinent Pangea was so colossal that its very existence dictated the laws of weather for the entire world. And just like the Appalachians, the Urals were born in the fires of a titanic collision of continents during the formation of Pangea, approximately 320–250 million years ago. The Ural Mountains arose when a landmass called Baltica, future part of Europe, collided with the Siberian continent and a smaller block known as the Kazakhstan terrain. These disparate continents were once separated by a narrow ocean, which paleogeographers call the Ural Ocean. As the oceanic crust slowly sank into the mantle and was remelted through subduction, the continents drew closer together until they finally collided, creating a new mountain range between them. While the history of the Urals is similar to that of the Appalachians, there are differences. Unlike the humid climate of North America, the Urals long experienced dry continental conditions. This helped the mountains retain some of their pristine ruggedness and rugged features, despite the ravages of erosion. Together, the Appalachians and the Urals, like two ancient monuments, bear witness to the incredible, slow, yet inexorable power of plate tectonics. They are a living record of Earth's history, silent storytellers of a time when entire continents drifted across the planet, colliding and lifting their rocky spines to the heavens. The Ural Mountains, stretching from the icy shores of the Arctic to the steppes of Kazakhstan, are more than just a geographic boundary dividing Europe and Asia. These ancient rocks hold a captivating and dramatic history of our planet's distant past. It is a veritable tale written in the language of stone. By carefully studying their rocks, geologists are discovering irrefutable evidence that the Urals were created by a massive collision of gigantic fragments of the Earth's crust. This catastrophe was like the collision of two enormous ships, which literally shattered upon impact. One of the key findings is the discovery of ophiolites in the very heart of the mountain range. Ophiolites are essentially chunks of ancient ocean floor and even fragments of the Earth's rocky mantle, which were incredibly forced onto the land surface. How is this possible? It could only have happened during a colossal tectonic collision, when the ancient ocean was caught in a vise, its floor crushed, fractured, and literally thrown onto the continental crust. This is direct evidence that millions and millions of years ago, a vast ocean stretched where the Ural Mountains rise today. But the Urals are more than just an open-air geological museum. They're also a veritable treasure trove. Deep beneath their majestic peaks lie shimmering veins of gold, glittering platinum inclusions, copper and nickel deposits, and even placers of beautiful gemstones. These mineral riches didn't arise by chance. They are a direct consequence of the vigorous geological activity that accompanied the mountain's birth. When tectonic plates collided, they generated colossal heat and pressure, leading to the formation of hot, mineral-rich solutions known as hydrothermal fluids. These flows seep through cracks in the rocks, leaching metals and depositing them in concentrated pockets. These conditions were ideal for the formation of valuable ores, and that's why the Urals have long been renowned as one of the richest mineral belts on the planet. In a deeper sense, the Urals can be compared to a scar on the Earth's surface, one that holds invaluable knowledge about the processes that shaped our planet. These mountain ranges serve as a perpetual reminder of how two completely different land masses were once connected. The Ural Mountains mark that very seam, the line where part of ancient Asia collided with part of ancient Europe. They formed the eastern boundary of the vast landmass known as Laurasia. Laurasia subsequently became the key northern portion of the supercontinent Pangea, which united almost all of Earth's land into a single gigantic world. But the Urals are only one chapter in this grand story. Throughout the globe, other mountain ranges sprouted like mushrooms after a rain during the formation of Pangea. Each was the result of devastating collisions. And here lies the most striking picture. If we could piece together the ancient map of Pangea like a jigsaw puzzle, we would discover that mountains scattered today across various continents, such as the Appalachian Mountains in North America, the Hercynian Belt in Europe, and even the Anti-Atlas Mountains in North Africa, were once links in a single, colossal, unified mountain system. This massive chain, known as the Central Pangean Mountain Belt, stretched across the heart of the supercontinent like the jagged spine of a gigantic beast. At the time, it was one of the most impressive sights on the planet, a world of majestic peaks, towering plateaus, and endless ridges rising thousands of meters. Pangea, this colossal continent that occupied a vast portion of the Earth's surface, dramatically altered the planet's climate with its emergence, and the echoes of those changes can still be seen today. Above all, the birth of Pangea led to global drying. Due to the continent's enormous size and the remoteness of its interior from the oceans, many areas became harsh and arid deserts. At the very heart of Pangea, there likely lay vast sun-baked lands where life was forced to adapt to extreme conditions. Imagine a world where climate was pushed to extremes. Summer was a time of unbearable heat, and winter brought bone-chilling frosts. In the very heart of the gigantic continent, far from the moderating influence of the oceans, extreme seasons reigned. These arid and harsh conditions gave rise to endless deserts and salt marshes, where evaporating water over millions of years left behind colossal layers of minerals, glittering in the ancient sun. However, move closer to the equator, and a completely different picture unfolds before us. Here, in the perpetual humidity, stretched dense, steamy jungles where colossal trees reached toward the sky. Giant ferns grew in lush carpets in the swampy lowlands. Over millions of years, the dying plants of these primeval swamp forests sank to the bottom, layer after layer, creating incredibly rich soil. Buried under the weight of subsequent generations, they eventually compressed and turned into those mighty seams of coal that humanity mines and burns today. Every ton of this black gold is a direct, tangible reminder of the lush and vibrant equatorial climate that once flourished on the supercontinent of Pangea. The birth of Pangea forever changed the face of the world's oceans. As the continents converged in a titanic embrace, the ancient seas that separated them disappeared. In their place arose a single, vast ocean that surrounded all land on the planet. Paleontologists have named it Panthalassa. This aquatic giant completely reshaped the pathways through which water circulated on Earth. Global ocean currents were rerouted along entirely new routes, dramatically affecting the distribution of heat and nutrients across the globe. Marine life had to hastily adapt to this new, changing world. As a result, entirely new species emerged, while others, unable to adapt, disappeared forever from the scene of life. The emergence of this supercontinent was accompanied by the birth of new, majestic mountain ranges. Imagine the collision of tectonic plates, a slow but inexorable process that lasted millions of years. Crushing the Earth's crust into gigantic folds, these mountains, barely emerging, immediately entered into an eternal battle with erosion. Wind and water, over countless centuries, wore down their peaks, and rivers carried rock particles and dissolved minerals into the world's oceans. This constant influx of sedimentary material altered the chemical composition of seawater, which, in turn, may have become a powerful driver of marine evolution. The saga of Pangea is a story that inspires awe. It is a tale of the incredible power of tectonic plates, slowly, centimeter by centimeter, smashing into each other over the course of not centuries, but hundreds of millions of years. The mighty mountains they created, like the Urals and the Appalachians, seem to us today simply as beautiful landscapes, but in reality, they are much more. They are physical scars on the face of the earth, eternal monuments to the ancient battles of the continents, and irrefutable proof that our world never stands still, but is always in motion and constantly changing. Understanding these grand mountain-building processes helps us comprehend not only the structure of our planet's surface, but also the powerful forces at work within its scorching depths. Amazing dramas unfold deep within the Earth. Plate tectonics, like an invisible cosmic machine, slowly but surely shapes continents, reshapes oceans, raises mountains, and even influences the very course of life's evolution. Pangea, once a single, indivisible supercontinent, marked a turning point in Earth's geological history. Its existence has affected every aspect of planetary life, from weather and climate to the emergence of new species and mass extinctions. Our Earth is not a frozen, lifeless ball of stone. It is a living, breathing world whose biography is etched in its rocks. Its past can still be read in the curves of mountain ranges, and its future is being written even now in the slow but inexorable movement of lithospheric plates beneath our feet. The very idea that all the known continents, North America, Africa, Eurasia, Australia, were once part of a single colossal landmass called Pangea, is one of the most captivating concepts in Earth science. Now, just imagine for a moment all the continents, separated today by thousands of kilometers of ocean, were once connected into a single whole. The spectacle is truly astounding. It sounds like the premise of a science fiction novel, but it's a real scientific theory that continues to captivate people to this day. However, for this incredible idea to be taken seriously by the scientific community, it required more than just a flight of fancy. It required irrefutable evidence. Geologists, scientists who study the structure and history of our planet, demanded reliable, testable answers to key questions. When exactly did all the continents merge? And what real evidence do we have to prove that Pangea actually existed? The answers to these questions didn't appear out of nowhere. They had to be slowly and painstakingly pieced together over many decades. Scientists, like detectives investigating an ancient mystery, studied rocks, fossils, and other clues left by the planet itself. Step by step, clue by clue, they pieced together a picture of the past. Today, the overwhelming majority of scientists agree that Pangea finally formed approximately 335 million years ago, during the period we call the Carboniferous. But this great unification of the continents wasn't an instantaneous event. It was the culmination of millions of years of slow and inexorable movement. Continents drifted across the planet's surface, colliding with one another as a result of massive geological cataclysms. This monumental merger created a landmass so vast that it influenced every aspect of life on Earth, from global climate to the evolution of the plants and animals that inhabited it. To understand when and how it happened, scientists had to become true forensic scientists. They examined rock layers, studied ancient fossils, and searched for hidden patterns in the Earth's magnetic field, frozen in stone. Some of the most compelling evidence comes from a field of science called paleomagnetism. This discipline studies ancient magnetism locked in rocks, allowing scientists to peer into our planet's past, like a time machine. Here's how it works. When certain rocks form, for example, when volcanic lava cools or particles settle on the bottom of bodies of water, they contain tiny minerals that act like compass needles, aligning themselves with the Earth's magnetic field. These minerals can be likened to myriad microscopic compasses, forever frozen in time. By studying rock samples from different continents and different geological eras, scientists can trace how exactly the continents moved over time. And their discoveries have been stunning. When they mentally arranged the continents into a single Pangea, all the magnetic data suddenly matched perfectly. The seemingly chaotic wandering of the magnetic pole, observed on each continent individually, formed a single, logical pattern. This became compelling, almost irrefutable evidence that these continents were once connected and shared the same magnetic history. Another crucial clue was hidden beneath the ocean floor. Scientists exploring the ocean floor discovered gigantic mid-ocean ridges, essentially seams in the planet's body, where molten rock rises from the depths and forms new crust. As this magma cooled, it recorded the direction of the Earth's magnetic field, just as rocks on land do. These records showed that the seafloor had been steadily expanding for millions of years, literally pushing the continents apart. There could only be one conclusion: if the continents are moving apart today, then in the distant past they were much closer or even formed a single entity. But magnetic data weren't the only trump card geologists had. There was also physical evidence right on the land surface: mountain ranges, rock layers, and landforms that matched perfectly despite the ocean separating them. One of the most striking examples is the Appalachian Mountains in eastern North America. When scientists mentally connected the continents into a mosaic of Pangea, these mountains turned out to be a direct continuation of the Caledonian Mountains in Europe and the Anta-Atlas mountain range in northwest Africa. All three mountain ranges were once part of a single, colossal chain known as the Central Pangean Mountain Belt. They didn't just line up, they had a strikingly similar geological structure. The composition of the rocks, their ages, and even traces of ancient deformations within them were virtually identical. It was like finding three fragments of the same torn tapestry in different rooms of a huge house. Another important clue came from studying the oldest land masses, known as geologic shields. This single landmass altered the direction of global winds and shaped climate systems on a planetary scale. In this merciless world, survival was a true test. Every living creature had to contend with scorching summer heat, followed by icy, bone-chilling winters, fierce, parching winds, and a constant, excruciating lack of water were the norm. To survive in such conditions, plants and animals had to possess incredible resilience, ingenuity, and sophisticated adaptations. Today, by studying ancient rocks, these fragments of the fractured Pangea, scattered across modern continents, we, like paleontological detectives, uncover traces of that ancient world. They tell us not only about the geography of the past, but also about monumental climate shifts. This is the story of how nature and land, acting in tandem, shaped the fate of all life. The story of Pangea is more than just a boring lecture on rocks and deserts. It is a powerful reminder of how the geography, shape, and size of a single continent could influence the very heartbeat of an entire planet. The Permian period was one of the most dramatic and transformative eras in Earth's long history. Each geological period is a crucial chapter in this book, filled with its own triumphs and tragedies. The Permian era, or simply Permian, lasted from approximately 299 to 252 million years ago. It was during this time that the supercontinent Pangea finally merged into a single, gigantic landmass, forever changing the face of the planet. These oldest and most stable parts of the continents, their foundations, fit together perfectly. When scientists compared them, they discovered that the Canadian Shield in North America fit seamlessly with the Baltic Shield in Europe and the West African Shield. These ancient land masses seemed designed for each other, like pieces of a single global puzzle. But perhaps the most exciting discovery came from the study of ancient glacial deposits. Scientists have discovered traces of ancient glaciers around the world, known as tillites, essentially fossilized glacial debris. The furrows and scratches in the rocks left by moving ice, as well as distinctive U-shaped valleys, can be found on vastly different continents that are now far apart: South America, South Africa, India, Australia, and even Antarctica. At first, this seemed like a scientific mystery, as many of these places are now located in warm tropical latitudes where glaciers could not possibly exist. However, When scientists combined all these lands in the southern part of Pangea into a supercontinent called Gondwana, everything fell into place. It turned out that all these continents were once clustered around the South Pole, where the existence of giant ice sheets would have been entirely natural. This became one of the earliest and most compelling pieces of evidence for the theory of continental drift. Finally, the rocks themselves tell stories of ancient climates. During the Carboniferous period, when Pangea was forming, vast swamp forests stretched along the equator. These forests left behind the richest coal deposits we still use today. Coal deposits can be found in North America, Europe, and parts of Asia, continents that are today separated by thousands of kilometers. However, if we combine them into a single supercontinent, Pangea, we find that all these coal-rich swamps line up in a single band along the ancient equator, where the warm and humid climate would have facilitated such rapid vegetation growth. Let's travel back in time and look at the land itself, at the rocks that hold the secrets of that era. In some places where warm swamps once swamped, we find layers of coal, a direct legacy of gigantic forests. But travel deeper into the ancient continent, and the picture changes beyond recognition. Here, in regions that would today be lifeless deserts, the land tells a completely different story. We discover deposits of minerals such as salt and gypsum, as well as characteristic red rocks rich in iron. All of these could only have formed under conditions of extreme drought, and most strikingly, these deposits are located precisely where the center of a gigantic supercontinent should have been, far from the moderating influence of the ocean. Such a clear distribution of climatic zones makes sense only if all the continents were once a single entity. But perhaps the most compelling evidence lies not in rocks, but in the fossilized remains of ancient life. Before us is Glossopteris, a remarkable fern-like plant with large tongue-like leaves. Its most distinctive feature, and the key to our mystery, lies in its seeds. They were too massive, too heavy to be carried across the ocean by the wind or to survive the long journey through salt water. And yet, Glossopteris fossils are found today in South America, Africa, India, Australia, and even in the icy wastes of Antarctica. The only reasonable explanation for this astonishing fact is that all these lands were once connected, allowing this plant to spread freely across a single landmass. And so, when we piece together all this evidence, traces of ancient magnetic fields, similar geological strata, climatic imprints, and of course fossils, a grand picture unfolds before us. We see how approximately 335 million years ago, during the lush Carboniferous period, the disparate continents of our planet began an inexorable convergence, merging into a single supercontinent, Pangea. This was more than just a geological phenomenon. It was a turning point that changed the face of the planet and forever determined the path of evolution. From the formation of the mountain ranges we see today to the fate of the ancient creatures that inhabited this single, vast world. One of the most striking pieces of evidence supporting this grand theory involves a tiny freshwater reptile called Mesosaurus. Imagine a creature no more than a meter long, about the size of a miniature dog. But size isn't the point. The key detail is that Mesosaurus was an inhabitant of freshwater rivers and lakes exclusively. Its fragile skeleton and entire biology were adapted to life in fresh water. The salty ocean was a deadly, insurmountable barrier. And here's where things get interesting. Mesosaurus fossils are found in only two places on the planet, southern Africa and the east coast of South America. Today, these places are separated by thousands of kilometers of the turbulent Atlantic, but in the distant past, they were obviously connected. Such a narrow habitat is a crucial clue, irrefutably proving that these two continents were once parts of a single whole. This is perhaps one of the most compelling pieces of evidence for the existence of ancient Pangea. Another compelling piece of evidence comes from the land reptile Lystrosaurus. This herbivorous lizard, the size of a modern pig, inhabited the planet during the late Permian and early Triassic periods, sometime between 252 and 248 million years ago. Unlike Mesosaurus, Lystrosaurus was a 100% land dweller and completely incapable of swimming. It couldn't have crossed even a wide river, let alone an ocean. However, its fossilized bones have been found in three incredibly distant places: Antarctica, India, South America, and Africa. The very fact that the same species of land animal once roamed freely across all these lands speaks volumes. These continents simply had to be connected. They formed the southern portion of Pangea, the gigantic landmass known as Gondwana. And crucially, the age of these fossils perfectly matches the time when geologists calculate that Pangea was fully formed. We can also add Cynognathes, another land reptile the size of a large dog, to this body of evidence. Like Lystrosaurus, it was completely incapable of sea travel. Again, its remains have been found on both sides of the Atlantic, in South America and Africa. Each such discovery is another nail in the coffin of the theory of separated continents. And the list goes on and on. Paleontologists around the world are finding striking similarities. The remains of ancient amphibians, other reptiles, the first clumsy mammals, and even entire fossil floras that are identical on continents separated today by thousands of kilometers of salt water. Most of these creatures were either purely land-dwelling or freshwater creatures, and they had no chance of crossing a vast ocean. These shared fossils tell us a clear and consistent story. Once upon a time, all the continents were fused together, and this story becomes absolutely compelling when we realize that it's supported by more than just fossils. And the formation of Pangea was just one act in this grand geological drama, setting the stage for everything that came after. Imagine a world in which traveling from one end of the world to the other meant not crossing an ocean, but a long journey across a single, gigantic continent. In such a world, the very idea of sea voyages between continents would be meaningless, because in those distant times, there was only one landmass on Earth, occupying almost an entire hemisphere. This was Pangea, the last great supercontinent, a single world that existed for tens of millions of years. Now let's peer into the very heart of Pangea. Imagine a place so far removed from the saving cool of the oceans that the very concept of a climate as we know it no longer applied. It was a world of extremes. Endless sun-baked deserts stretched for thousands of kilometers. There was no soothing sea breeze. Instead, there was unbearable daytime heat, followed by icy nighttime cold and an eternal, relentless drought. To understand why this happened, we need to understand the scale of Pangea. It stretched from one pole to the other. Modern continents, even giants like Asia and Africa, are still influenced by oceans, which bring rain and stabilize temperatures. But Pangea was so vast that it created a unique climate phenomenon known as continentality, taken to its absolute extreme. The moist air rising over the great Panthalassa Ocean or the warm Tethys Sea had to travel thousands of kilometers to reach the center of the supercontinent. But along the way, it lost all its moisture. Rain fell on the coastal regions, while only dry, hot winds reached the interior, making the already harsh conditions even worse. As if that weren't enough, Pangea's interior was sealed off from the world by gigantic mountain ranges. These were the scars left by the titanic collision of continents. Imagine the might of the Appalachians in North America, the Scottish Highlands, or the ancient mountains of Europe. In those distant times, they weren't just hills, but young, jagged peaks that rivaled the modern Himalayas in height. These colossal barriers became the final obstacle to any moisture attempting to penetrate the continent's interior. Life found itself at a crossroads: adapt or die. At the beginning of the Permian, some ancient marsh plant species still clung to life, finding refuge along rivers and in damp coastal zones. Giant club mosses, such as Lepidodendron and Sigillaria, still towered here, veritable prehistoric skyscrapers of the plant world. Sphinopsids, distant relatives of modern horsetails, completed the picture. In those distant times, the landscape was adorned with astonishing calamites resembling giant bamboo groves and countless species of ferns. These plants thrived in the moist soil, forming dense thickets that, millions of years later, compacted into the very coal seams that humanity uses today for fuel. But the world was changing inexorably. Rainfall became increasingly rare and unpredictable, and the difference between summer and winter temperatures became more extreme. Moisture-loving flora began to lose ground. They were replaced by new masters of the land, gymnosperms, perfectly adapted to the harsh and arid lands of Pangea. These include the familiar conifers, as well as cycads and ginkgos. Gymnosperms enjoyed a colossal evolutionary advantage. Their primary weapon was their seeds, not their spores. A seed, protected by a coat, could survive months of drought and germinate only when rain returned. Furthermore, wind-borne pollen freed them from the need to reproduce in standing water as their predecessors had. Their leaves were tough, covered in a waxy coating that significantly reduced moisture evaporation, an ideal design for survival in deserts and arid forests. One of the most iconic and important plants of the Permian period was Glossopteris. It belonged to a group of seed ferns, amazing creatures that combined features of both ferns and seed plants. Its broad leaves had a distinctive tongue-like shape. These plants formed dense forests in the south of Pangea, in a region scientists call Gondwana. These forests covered what are now South America, Africa, India, Antarctica, and Australia. Fossils of Glossopteris found on all these continents, now separated by oceans, became one of the key pieces of evidence for Alfred Wegener when he proposed his revolutionary idea of continental drift. This theory helped science realize that Pangea really existed. glossopterous forests played a vital role in Permian ecosystems. They provided shelter, food, and habitat for countless animals. Their shade provided shelter and nesting sites for many creatures, especially herbivores that fed on their succulent leaves and nutritious seeds. The fauna of the Permian period was no less astonishing and bizarre. This was a time when synapsids reigned supreme on land. It's important to understand that they weren't reptiles in the traditional sense, but they hadn't yet become mammals either. They represented the very evolutionary lineage that would one day lead to us. That's why they're often called thermid-like reptiles. In the early Permian, a group called the pelycosaurs dominated the scene, and of course the most famous member of this group is Dimetrodon, a predator unmistakable due to the enormous sail-like crest on its back. What did it use this amazing adaptation for? Scientists believe it may have served as a kind of radiator. In the morning, the sail helped absorb solar heat more quickly, and in the middle of the day, it released excess heat, preventing overheating. Pelycosaurs were incredibly diverse, ranging from large predators to small insect hunters. But as time went on, pelycosaurs gave way to a more advanced group of synapsids known as therapsids. These creatures were already one step closer to mammals. They possessed powerful jaws, specialized teeth, and a more sophisticated method of locomotion. Some of them, in their structure and behavior, were already strikingly reminiscent of modern animals. Among them, the Danocephalians stood out among the largest animals of their time. Some were peaceful, giant herbivores with incredibly thick skulls like Asteminosuchus, whose head was crowned with bizarre horn-like bony protrusions. Others were ferocious predators like Ankylosaurus, a natural-born killer. Their fossils have been found in diverse locations, from South Africa to Russia, demonstrating how widespread they were across Pangea. Another large and successful group were the Dicynodonts, strange, fanged herbivores. Its name is Pangea, and its history takes us back hundreds of millions of years, deep into Earth's geological past. Pangea's history begins in the hoary antiquity of the Paleozoic era, long before dinosaurs reigned supreme. The process of its formation was titanic, incredibly slow, yet inexorable. It began approximately 335 million years ago during the Carboniferous period. At that time, the world was already divided into several large continents, which, driven by invisible forces, began their great march toward each other. Two giants dominated the global stage at that time, Gondwana and Laurasia. Gondwana, that southern giant, encompassed the lands that would eons later become South America, Africa, Antarctica, Australia, and India. Northern Laurasia included the future North America, Europe, and much of Asia. Millions of years later, these colossal tectonic plates inexorably converged, driven by powerful processes hidden in the Earth's molten mantle. Like pieces of a gigantic mosaic, they converged, enclosing ancient oceans and compressing into a single, monolithic landmass. Thus was Pangea born. Pangea reached its peak and greatest unity during the Permian period, and it remained in this form until the dawn of the dinosaur era. A particularly vibrant chapter in its history was the Triassic period, which spanned from 299 to 200 million years ago. This was truly Pangea's golden age, when most of the planet's land masses were consolidated into this vast continent. They ranged in size from small dog-sized burrowers to true giants, comparable to modern hippos. They had a horny beak, ideal for shearing tough vegetation, and a pair of distinctive tusks, for which they earned their name. But the true star of this group, the champion of survival, was Lystrosaurus, whose name translates as two-fanged lizard. Its fossils have been found on every continent that once made up Gondwana, including Antarctica. This provides further compelling evidence of how closely connected these regions were in the past. Lystrosaurus's ability to dig deep burrows likely helped it survive severe droughts and hide from ruthless predators. Speaking of predators, the Gorgonopsians truly terrified the inhabitants of the Permian world. These creatures, with long, saber-like fangs and powerful jaws, were at the top of the food chain. Predators like Gorgonops and Inostrancevia were the top apex predators in their ecosystems, hunting herds of clumsy dicynodonts. While synapsids were the stars of the Permian, other reptiles weren't far behind. Large armored pariasaurs like Scutosaurus scurried slowly across the ground. These creatures resembled living tanks, a cross between a giant turtle and an armadillo. And in the undergrowth, small, agile reptiles like procolophonids scurried about. In the late Permian, the ancestors of the future rulers of the world, dinosaurs and crocodiles, began to appear on the scene. Their group, the Archosauromorphs, was still small in number and played a minor role compared to the dominant therapsids. But their time was not far off. Amphibians didn't disappear either, especially in humid regions. Giant crocodile-like creatures known as temnospondyls inhabited rivers and lakes. The air was filled with the buzz of a multitude of insects, cockroaches, dragonflies, and the very first species of beetles flitted through the forests and deserts. The colossal size and integrity of Pangea had a profound impact on all of these creatures. Here's how it worked. A single, gigantic continent dramatically altered the climate, winds, and ocean currents. The heart of Pangea became a vast, scorching desert, while the coastal regions remained wetter. This created incredible evolutionary pressure, forcing plants and animals to adapt to increasingly harsh conditions. The lack of ocean barriers allowed animals and plants to migrate freely over vast distances. This is why species like Lystrosaurus and Glossopteris were able to spread across entire continents. Today, scientists use these fossils as markers to understand how exactly the continents were connected in the distant past. But unfortunately, let's fast forward 250 million years into the past, to the very end of the Permian period. The planet stood on the brink of a catastrophe of unprecedented proportions. What triggered this tragedy still remains a mystery to scientists. Perhaps it was a series of monstrous volcanic eruptions, a global climate collapse, or some other unknown factor, but the result was horrific. For 9 out of 10 species living in the world's oceans, and for 7 out of 10 land creatures, it was a death sentence. Entire ecosystems were wiped off the face of the earth in the most devastating extinction event in the planet's history. But in this deafening silence, amid the ashes of the old world, the seeds of new life were already sprouting. The dawn of a new era, the age of dinosaurs, was breaking on the horizon. Imagine a world without the familiar continents. All the planet's landmass merged into a single, colossal supercontinent. which scientists named Pangea. This massive unification of the Earth's crust, which existed from approximately 299 to 252 million years ago, was more than just a geographic oddity. It radically rewrote the rules of the game for all life on Earth. This event impacted animal lifestyles, plant habitats, and the very course of evolution. Perhaps the most crucial consequence was that the formation of Pangea triggered a great mixing of species. Almost all land masses were united, and there were no longer gigantic oceans to serve as insurmountable barriers to animal migration or plant dispersal. Species that had previously evolved in isolation for millions of years, separated by vast expanses of water, were now able to cover enormous distances. Animals could roam freely across the planet, and wind and currents carried plant seeds to the most remote corners of the world. This led to a striking effect that paleontologists call provincial decline. Unique, endemic species in certain regions began to disappear. Typically, when continents are fragmented, evolution follows its own unique path on each. But during the Pangea era, the same or very similar creatures inhabited vast territories. The best evidence of this is the fossil remains of the plant Glossopteris and the fanged herbivore Lystrosaurus. Their bones and leaf imprints have been found in South America, Africa, icy Antarctica, and even India, landscapes that today are separated by thousands of kilometers of turbulent ocean. This clearly demonstrates how closely connected the world of Pangea was. In the supercontinent's vastly different climate zones, we find similar plant and animal species that played similar roles in their ecosystems. This made the planet's environment more homogeneous than ever before or since. Pangea was not only vast in area, but also incredibly diverse in climate. Stretching from the North Pole to the South Pole, it created vast and often extreme weather patterns. The heart of this gigantic continent, its interior, lay vastly removed from the moderating influence of the oceans. It was a sun-baked, scorching desert. However, on the coasts, the climate could be much milder, and life thrived thanks to powerful seasonal rainfalls that we would today call monsoons. To survive in this world of extremes, living creatures had to resort to incredible tricks. In the plant kingdom, gymnosperms, the ancestors of modern conifers, came to the fore. Their tough, waxy leaves and hard-shelled seeds were the perfect weapon against drought. They were the ones who conquered the parched interior of Pangea. Meanwhile, older, more moisture-loving plants, like those that once formed the giant Carboniferous forest, could now only survive in narrow coastal zones or deep river valleys where moisture was abundant. Animals also had to change dramatically. Many Permian synapsida, the distant ancestors of mammals, developed complex survival mechanisms in harsh conditions. Some likely escaped the scorching heat by digging deep burrows. Others were forced to change their diet, switching to more readily available and nutritious food sources. Because climate zones stretched for thousands of kilometers, the same adaptations allowed completely different species to survive in the vast expanses of Pangea. This unified Earth became a single, continuous migration highway. Animals were no longer confined to a single continent. If conditions around them changed, becoming too dry or, conversely, too cold, they could simply pack up and migrate to more favorable lands. Some species apparently traveled thousands of kilometers in search of food, water, and mates. This freedom of movement helped them survive and thrive, escaping harsh conditions and following changing climate zones. As a result, different species could inhabit the same regions. However, this also had a downside. Competition in some areas increased dramatically. Predators could now pursue their prey over thousands of kilometers, turning the life of herbivores into an endless race for survival. Life on land acquired a new, previously unseen level of complexity. Ecosystems became interconnected into a single, continental-scale network. There was another curious side effect of Pangea. The lack of isolation meant fewer new species emerged. One of the main drivers of evolution is the separation of populations by geographic barriers, be they oceans, mountains, or deserts. Isolated, groups evolved differently over time, giving rise to new species. Scientists call this process allopatric speciation. But on Pangea, there were far fewer such natural barriers than today. While there were rivers and mountain ranges, they weren't enough to separate animal populations for long. As a result, species remained genetically related across vast expanses, with fewer opportunities for independent evolution. This likely led to a decline in overall biodiversity on the planet. There were fewer species than during the eras of fragmented continents, although each was much more widespread. Thus, Earth's ecosystems became more closely interconnected, but also more homogeneous. Nevertheless, the presence of such a vast land mass provided a powerful impetus for the development of terrestrial ecosystems, which grew in size and complexity. The center of life shifted from the oceans to the continents. The Permian period was a time of great innovation. New life forms continually appeared on land. One of the most successful groups was the Therapsids, Therapsida, sometimes inaccurately called therapsids. These creatures were distant relatives of mammals and thrived in the dry, seasonal landscapes of Pangea. The plant world was undisputedly dominated by gymnosperms, such as the early ancestors of pines and cycads. Together, they breathed life into vast expanses of land, transforming lifeless plains and deserts into vibrant ecosystems. And while marine life continued to evolve, the epicenter of evolution had clearly shifted to land. Here, new challenges and opportunities shaped life in unprecedented ways. However, the very interconnectedness that allowed species to spread across the globe also made them incredibly vulnerable to global catastrophes. Because all ecosystems were part of a single chain, a single catastrophic event could ricochet across the entire planet, and that is precisely what ultimately happened. The denouement came at the end of the Permian period, about 252 million years ago. Massive volcanic eruptions, known as the Siberian Traps, erupted in what is now Siberia. They released unimaginable amounts of carbon dioxide into the atmosphere. This likely triggered rapid global warming, making many regions of the planet too hot and dry to survive. Since Pangea was a single, relatively homogeneous continent, there were very few isolated refuges where species could survive the catastrophe. When the climate became a death trap, they had no choice but to perish. Thus began the Permian-Triassic extinction event, the most devastating in Earth's history. About 90% of all marine species and approximately 70% of all land vertebrates were forever wiped off the face of the planet. The story of life on Pangea is a grand drama of incredible unity and colossal vulnerability. The unification of the continents created a world where the destinies of animals and plants were intimately intertwined, where their fates depended on the slightest changes in the global environment. They were free to roam the planet, where new types of terrestrial ecosystems were born, and adaptation to harsh and arid conditions became the key to survival. But this same interconnectedness turned tragic. When catastrophe struck, no corner of the world could escape it. Pangea vividly demonstrates how the slow dance of tectonic plates can alter the fate of a planet, for better or for worse. Life on this supercontinent was simultaneously a triumph of evolution and its greatest tragedy, an object lesson in the ever-changing nature of our Earth. Imagine a time in the distant past when life itself on our planet came within a hair's breadth of annihilation. This wasn't just a local disaster like a volcanic eruption or a devastating hurricane. No, this was a total crisis on a planetary scale. The mass extinction was so devastating that it wiped out 90 out of every 100 species living in the ocean, and on land, 70 out of every 100 animal species. This chilling moment in the Earth's annals occurred approximately 252 million years ago and is known to science as the Permian-Triassic extinction event. But it also has another far more ominous nickname, the Great Dying. And this name is no exaggeration. Of all the catastrophes that have shaken our planet in its 4.5 billion years of existence, this was the most devastating. It was the greatest test in the history of our planet, the harshest of all. It was as if all life on Earth was being forced through the eye of a needle, a narrow and deadly corridor that offered only a ghost of a chance for salvation. The vast majority of species never made it all the way, and for those few lucky ones, it took millions of years to recover from the shock and begin to rebuild the devastated world. But before we delve into the darkest details of this planetary cataclysm, let's take a step back. Transport ourselves for a moment to the world as it was moments before it was wiped off the face of the Earth. In those distant times, our planet looked completely different. Imagine all the modern continents merging, forming a single colossal landmass that scientists call Pangea. This supercontinent stretched from the North Pole's ice cap to the southernmost latitudes. This unique geography created completely different climate conditions and ocean currents. The central regions of Pangea, thousands of kilometers from the moderating influence of the oceans, were vast, sun-baked deserts. Rain was rare, and temperatures could swing wildly from daytime heat to nighttime chill. However, life clung to the coastal zones. The climate along the coast was much more hospitable, in places even resembling a tropical climate, with distinct alternations between wet and dry seasons, similar to modern monsoons. And despite these harsh conditions, life flourished. The oceans of that time literally teemed with an incredible diversity of creatures. Invertebrates were especially numerous. Ammonites, with their coiled shells, brachiopods, bryozoans, and entire underwater cities of colorful coral reefs. On land, a group of animals known as synapsids reigned supreme, the ancient ancestors of all mammals, including us. Among them were both fearsome predators and peaceful giants. However, nothing, not even a supercontinent, lasts forever. The same forces that once stitched worlds together eventually began to tear them apart. Around 175 million years ago, in the mid-Jurassic period, the first treacherous cracks began to appear across the surface of Pangea. With each passing millennium, they grew wider and deeper, first becoming gaping fissures and then newborn oceans. Over time, these gigantic scars divided the single Earth into smaller continents, which slowly drifted toward their present locations, forming the familiar contours of North and South America, Africa, Europe, Asia, Australia, and Antarctica. This was the birth of the world as we know it. But why is Pangea so important to us, given that it disappeared long before humans appeared? The answer lies in its colossal influence on geology, climate, and the very evolution of life on Earth. When ancient continents collided to form a supercontinent, the Earth's crust was crumpled like paper. These massive collisions gave rise to some of the most ancient and majestic mountain ranges in the world. Look at the Appalachian Mountains in eastern North America, the Caledonian Mountains in Europe, or the Ural Mountains dividing Europe and Asia. These aren't just mountains. They are scars left by a titanic collision of worlds. These rugged peaks are silent witnesses that still remind us of Pangea's former might. We see mighty gorgonopsids, merciless hunters with saber-like fangs, stalking more docile herbivores, armed with beaks and tusks for defense. But perhaps one of the most common creatures of that era was Lystrosaurus, a stocky, pig-sized herbivore, fate destined for the incredible role of becoming one of the few survivors of the coming apocalypse. The land was covered in dense forests of conifers, giant ferns, and other prehistoric plants, forming complex ecosystems with intricate food chains. That world may not have been as vibrant and colorful as our modern Earth, but it was full of energy. The planet literally pulsated with life. However, deep within the planet's molten core, powerful forces were already gathering that would soon unleash unimaginable destruction upon this world. The most likely culprit of that global catastrophe was a series of titanic volcanic eruptions in the territory we now know as Siberia. And this wasn't just a single volcanic eruption. Imagine an entire region known as the Siberian Traps, where lava didn't erupt from the conical mountains we're accustomed to. It oozed, burst forth from gigantic fissures in the Earth's crust, stretching for hundreds of kilometers. And this madness continued not for days or years, but perhaps for 1,000,000 years. Imagine this scene: fiery rivers of molten rock erupting from gaping cracks in the earth, drenching everything around them. These eruptions formed gigantic sheets of solidified basalt rock, more than 1 kilometer thick in some places. Over the course of millennia, colossal quantities of lava poured onto the surface, millions of cubic kilometers according to scientists. This volume would be enough to cover entire continents with a thick layer of rock. But the lava itself was only part of this deadly symphony. These eruptions released monstrous quantities of gases into the atmosphere, primarily carbon dioxide and sulfur dioxide. Sulfur dioxide, reaching the upper atmosphere, can reflect sunlight, causing short-term cooling. But carbon dioxide, on the other hand, acts like a blanket, trapping heat and creating a greenhouse effect. And over time, this effect became dominant, turning the Earth into a scorching hothouse. But the worst was yet to come. The lava wasn't just erupting through pure rock. Along the way, It was burning through vast underground deposits of coal, oil, and salt. This process triggered the release of even more dangerous compounds. Methane, a greenhouse gas many times more potent than carbon dioxide, poured into the atmosphere, along with chemicals like chlorine and fluorine, capable of poisoning all life. The perfect formula for disaster had formed. It was an atmospheric collapse the likes of which Earth had never seen. At first, a massive sulfur release may have triggered a brief volcanic winter, briefly cooling the planet. But this was only a deceptive respite. Continued and massive emissions of carbon dioxide and methane triggered an irreversible process. The planet's temperature began to rise rapidly. In a geologically short time, the average global temperature likely jumped by more than 10 degrees. This was enough to transform rainforests into lifeless deserts and render tropical regions completely uninhabitable. Such a sharp warming left animals and plants no chance to adapt. Forests dried out, rains ceased, and vast tracts of land became covered with deep cracks. Plants withered and died. Herbivores, deprived of food, followed suit. And soon after, the predators that preyed on these herbivores began to disappear. The situation worsened with each passing day. The food chain collapsed link by link. But perhaps the most terrible tragedy unfolded in the depths of the world's oceans. As water warmed like flat lemonade, it could no longer hold as much oxygen. And oxygen is as essential to marine life as air is to us. The warmer the oceans became, the less oxygen remained, leading to the formation of gigantic dead zones. On top of that, massive amounts of carbon dioxide from the atmosphere dissolved into the water, making the oceans more acidic. This made it virtually impossible for creatures like corals, mollusks, and plankton to build their shells and skeletons. And without these tiny but vital organisms, the entire marine ecosystem began to collapse like a house of cards. This deadly change did not go unnoticed. Anoxic zones, places completely devoid of life, began to rise higher and higher. They encroached on shallow areas, turning once thriving marine ecosystems into silent underwater graveyards. Fish, corals, mollusks, and other marine life that once inhabited these waters began to die off in colossal numbers. But the horrors didn't end there. These dead, oxygen-free waters began to feast on new hosts, strange anaerobic bacteria known as green sulfur bacteria. They don't require oxygen to survive. As they thrive, these microbes produce hydrogen sulfide, an extremely toxic gas with a foul, rotten egg smell. As this gas accumulated in the oceans, a new nightmare was born. Scientists call this condition euxinia. When the water is deprived of oxygen and filled with toxic hydrogen sulfide, the oceans stop being simply lifeless. They become active killers, deadly to all life. Traces of this nightmare can be found in the geological record across the globe. Scientists are discovering layers of black shale rich in organic matter and sulfur, a clear indication that those same toxic waters once existed here. It's as if the Earth has preserved memories of a time when its oceans darkened, became fetid, and deadly to almost all life. The consequences were catastrophic. Tiny plankton, the base of the food chain, disappeared. Coral reefs collapsed. Large fish and even the ocean's top predators perished. Some were poisoned by hydrogen sulfide, others simply suffocated. Even the thermocline, The invisible boundaries separating warm surface waters from the cold depths shifted upward. This process took time, but eventually the waters near the surface began to experience a lack of oxygen, turning from a cradle of life into death zones. Ocean ecosystems that had taken millions of years to build were destroyed practically overnight. Then the situation got even worse. Scientists believe the hydrogen sulfide didn't stay locked up in the oceans. Some of this toxic gas escaped into the atmosphere. This gas could not only have poisoned land animals, but also seriously damaged the ozone layer, our planet's protective shield. Imagine our planet's protective dome, the ozone layer, which carefully protects all life from harmful ultraviolet rays. Now, imagine this shield weakening and disappearing. Sunlight, once the giver of life, turns into a deadly weapon. It scorches vegetation, incinerates animals, and may well have been one of the causes of the mass extinction of all life on land. A brutal chain reaction unfolds before us. The poisoned oceans strike the skies, and the skies in turn unleash new torrents of death upon the earth. But this nightmare was only part of a global catastrophe. It cannot be attributed to any one specific event. It was a whole series of interconnected disasters, each one only intensifying the previous one. The epicenter of this nightmare was the so-called Siberian Traps, a gigantic region in what is now Russia. Let's fast forward 252 million years into the past. Here, in this very spot, volcanic eruptions of unimaginable scale began. For nearly 1 million years, these volcanoes spewed molten lava and toxic gases from the planet's depths, releasing colossal volumes of carbon dioxide into the atmosphere. As a result, the planet began to rapidly warm. But this was only the beginning of the apocalypse. As global temperatures rose, ice formations deep in the ocean floor and permafrost began to melt, trapping methane. These natural reservoirs held a gas that is many times more potent than carbon dioxide in its greenhouse effect. And when this methane began to be released, warming accelerated exponentially. It was like adding fuel to an already raging global fire. Some scientists also theorize that these massive volcanic eruptions were the primary cause of global warming. The situation was exacerbated by forest fires fueled by drought and atmospheric changes, releasing even more carbon into the air. Ocean currents slowed, leading to a catastrophic drop in oxygen levels in the seas. All this set off a deadly cycle of events: scorching oceans, toxic gases in the atmosphere, a total lack of oxygen, and a poisoned sky. The planet found itself trapped in a deadly cycle, where each disaster begat the next. The consequences of this cataclysm reached a scale the Earth has never seen before or since. About 90% of all marine species simply vanished. On land, approximately 70% of all vertebrates, that is, animals with skeletons, disappeared. Ancient creatures that had thrived for hundreds of millions of years were wiped off the face of the planet. The famous trilobites, whose history began in the Cambrian period, vanished forever. Blastoids, distant relatives of sea lilies, became extinct. Numerous species of brachiopods, crinoids, and ammonites either became extinct or were on the brink of extinction. During that terrifying period, only a handful of species managed to cling to life. On land, giant predators like the fearsome gorgonopsids were completely wiped out. Only a few, the most resilient creatures, survived. Among them was Lystrosaurus. Picture a squat, pig-sized animal with a barrel-shaped body and a reptilian appearance. It was one of the few survivors. Even among the once dominant synapsids, the group that would later give rise to all mammals, most species vanished into oblivion. The entire complex and fragile web of life on the planet was torn to shreds. Scientists call this phenomenon selective extinction. Some creatures were able to adapt to the inferno, the lack of oxygen, or the acidified ocean waters, but the vast majority succumbed to these challenges. Those that survived did so through incredible luck, exceptional endurance, or some unique adaptation. When the worst was over, the Earth sank into a period of deathly silence. The early Triassic period arrived, a time paleontologists sometimes call the dead zone. Life was reduced to a few surviving species. Only the fittest survived. Most animals were tiny, a phenomenon known as the Lilliputian effect. Large animals simply couldn't survive in the harsh conditions of the New World. The planet was dominated by so-called catastrophic species, like Lystrosaurus, which managed to survive where almost nothing else could. Millions of years passed before life began to slowly rebuild from the ashes. But the world that eventually emerged was a completely different place. The great dying left behind empty ecological niches. These were vacant spaces in nature that, over time, began to be filled by new evolving species. This slow and painful process of recovery ultimately led to the rise of the dinosaurs, and much later, the mammals. Thus, on the ruins of the old world destroyed by the great dying, the foundations of all modern life were laid. Even today, scientists continue to study this incredible event. Using cutting-edge instruments, they examine ancient rocks and sediments in search of chemical traces that could reveal what truly happened 252 million years ago. They meticulously compare the dates of volcanic eruptions and monitor climate changes and oxygen levels in ancient oceans. By creating sophisticated computer models, researchers are attempting to reconstruct how this tragedy unfolded. And while some details remain controversial, most experts agree. The eruptions of the Siberian traps were the first impetus for a global catastrophe. The Great Permian extinction wasn't just the end of an era, it was a complete reset of life on Earth. It's a terrifying reminder of how tightly interconnected all of our planet systems are and how quickly everything can collapse if this delicate balance is upset. From poisoned oceans to skies filled with deadly gas, 252 million years ago, the world faced a catastrophe that nearly extinguished the very spark of life. But from these ashes, after a long and painful struggle, life rose again. It became more humble, but ready to begin an entirely new chapter in the planet's history. Imagine Earth slowly recovering from the greatest biological catastrophe in its history. This is precisely what the world was like at the dawn of the Triassic period, which began about 252 million years ago and ended about 201 million years ago. The planet had just survived the Permian-Triassic extinction event, an event so devastating that it wiped out nearly all life in the oceans and a vast majority of species on land. And later, as Pangea began to crack at the seams and disintegrate, an equally monumental event occurred. New oceans began to form. As the continents drifted apart, molten rock rose from the depths of the earth, pouring onto the surface solidifying and creating an entirely new ocean floor. This is how the Atlantic Ocean began to form, and this process hasn't stopped. It continues today, slowly, centimeter by centimeter, pushing the continents apart and changing the face of our planet. The climate during Pangea was a world of extremes completely unlike our own. The supercontinent was so vast that its interior lay thousands of kilometers from the nearest coast. This meant that the moderating sea breezes simply couldn't reach it. The result? Summers were unbearably hot and dry, and winters were piercingly cold. The heart of Pangea was likely a gigantic dusty desert. The ocean surrounding this unified world was called Pontalassa, a vast, deep superocean. With no continents to block the currents, warm water circulated freely along the equator, making the planet as a whole even hotter. This led to extreme weather patterns, including monstrous seasonal monsoons that dumped torrents of rain on the coasts, leaving inland areas completely dry. But perhaps Pangea's most astonishing legacy is the history of life itself. The fact that all land was connected had incredible consequences for evolution. Vast areas were covered in deserts, scorched by the merciless sun. However, not all regions were lifeless. Studies of ancient rocks show that some coastal areas were subject to powerful seasonal monsoons, intense storms that brought short but intense downpours. Throughout the Triassic period, the Earth's climate was very warm. There were no ice caps at the poles, and the ocean waters were relatively warm and calm, still recovering from the Great Dying. The lack of cold currents led to low oxygen levels in the oceans, posing serious challenges for marine life. After the devastating extinction, Earth appeared barren and desolate. At the beginning of the Triassic, the plant world was dominated by a few of the hardiest and fastest growing species, such as the strange, spindly Pleuromaea, a type of primitive fern. However, as time passed, life gradually reclaimed its position. By the mid to late Triassic, the planet was once again covered in forests. Tall conifers, cycads, palm-like plants, and ginkgo trees spread across the landscape, providing shelter and food for the growing animal population. These forests became the foundation for the formation of more complex food webs and healthy ecosystems. Immediately after the Permian extinction, Earth's ecosystems were primitive and simple, dominated by just a few species that were fortunate enough to survive. Paleontologists call these resilient organisms catastrophe taxa because they survived the worst extinction in history. One of the most famous examples is Lystrosaurus, a strange pig-sized creature with a barrel-shaped body, short fangs, and a bulldog-like snout. Lystrosaurus was a member of the Dicynodonts, a group of herbivorous animals from the order Synapsid, distant relatives of mammals. This unassuming yet incredibly resilient creature managed to spread across the planet. Remains of this amazing creature have been discovered in diverse locations, from the icy wastes of Antarctica to the scorching lands of South Africa, India, and China. In those distant times, all these continents were fused into a single southern supercontinent known as Gondwana. It's no wonder this creature earned the nickname Triassic Ark. Lystrosaurus owed its survival to a unique set of skills. It was completely unpretentious in its diet, a true master at digging deep burrows to hide from danger, and, most importantly, it apparently could survive in an atmosphere with extremely low oxygen levels. These unique qualities gave it a colossal advantage in the harsh and devastated world of the early Triassic period. As the planet slowly healed from the Great Extinction, new players began to emerge onto the scene. New groups of reptiles emerged and rapidly diversified. Among them, the archosauromorphs stood out, a grandiose group of lizards that would later give rise to both mighty crocodiles and the legendary dinosaurs. Imagine these early representatives. They resembled swift, long-legged lizards. While dinosaurs were just taking their first steps on their evolutionary path, another branch of archosaurs reigned supreme on Earth: the pseudosuchians, ancient and terrifying relatives of modern crocodiles. This group included a whole gallery of amazing and deadly creatures. Among them were the phytosaurs, outwardly resembling crocodiles, but with nostrils positioned high on their heads, allowing them to breathe while almost completely submerged. There were also the etiosaurs, true living tanks, herbivorous giants clad in heavy bony armor from head to tail. And on land, the rauisuchians, ferocious predators that walked on straight legs and looked like giant running crocodiles, were a terror. These animals were the top predators and dominant herbivores in the Triassic world, while the first dinosaurs timidly remained in their shadow, patiently biding their time. While this drama unfolded, another group of creatures quietly watched from the sidelines, experiencing their own unseen evolutionary revolution. These were the cynodonts, the direct ancestors of all mammals that once ruled the world during the Permian. By the beginning of the Triassic, most of their relatives, the synapsids, had been wiped off the face of the Earth in the Great Extinction, but a few managed to survive. And these survivors, the cynodonts, began to undergo subtle but incredibly important changes. They developed specialized teeth, sharp incisors for biting, pointed canines for holding, and flat molars for grinding. This dramatically improved their chewing ability, which was critical for creatures with a high metabolism. They also developed a secondary palate, a bony partition separating the airway from the mouth. This ingenious invention of nature allowed them to breathe and chew simultaneously. Their lower jaw also began to change. Some bones shrank in size and eventually migrated into the middle ear cavity, becoming part of it, a key feature of all true mammals. Fossils of cynodonts, such as Thrinaxodon and Cynognathus, clearly demonstrate this transitional stage. These creatures still resembled reptiles in many ways, but they were already beginning to look and behave like mammals. Some scientists believe they were already warm-blooded and even possessed features such as whiskers and fur, which gave them a huge advantage in colder and more unpredictable climates. The Triassic period was an era of great trials and dramatic transformations, a time of total destruction followed by incredible rebirth. During this period, Earth recovered from the most terrible catastrophe in its history and became a cradle for new, powerful life forms that would shape its entire future. Dinosaurs began their long and arduous journey to global domination, while our distant ancestors, the ancestors of mammals, gradually honed the traits that would one day lead to the emergence of humans. Earth was a scorching furnace beneath the blazing sun of a gigantic supercontinent, and bizarre and formidable reptiles roamed its vast expanses, both on land and in the water. It was a remarkable time of transition, a veritable laboratory of evolution where the future masters of the planet were forged. Near the end of the Triassic period, about 201 million years ago, after long eons of gradual but inexorable change, something truly astounding occurred. It was the moment when the very first true mammals appeared on Earth. These ancient creatures were incredibly small, often no larger than a modern mouse or shrew. They likely spent most of their lives under cover of darkness, foraging only at night, when the weather was relatively quiet and they could hide from the larger, more dangerous reptiles that patrolled the world during the day. Their tiny size and nocturnal lifestyle were not just a coincidence, but a brilliant survival strategy. By remaining invisible and active at night, these tiny mammals could avoid direct competition with the massive and fearsome archosaurs that dominated the daylight. Instead of fighting over the same prey, they found their own secluded niche in the food chain, hunting insects and other small invertebrates, creatures that the giant reptiles either overlooked or simply couldn't catch. Although these tiny mammals lived alongside enormous dinosaurs and terrifying predators, they didn't simply hide in the shadows. They forged their own unique evolutionary path. During this time, they developed a whole host of distinctive traits that would one day define the entire mammalian lineage: warm-bloodedness, the ability to nurse their young, incredibly sensitive hearing, and a proportionally larger brain relative to their body size. These traits didn't yet make them a dominant force, but they laid a solid foundation for the future greatness of mammals, which would only come millions of years later, after the age of dinosaurs had reached its fiery end. The Triassic period, which spanned approximately 252 to 201 million years ago, was a time of constant change and fierce competition. Earth was still recovering from the most devastating mass extinction in its history, and life slowly but surely filled the resulting ecological voids. Throughout the decades of the Triassic, a diverse group of reptiles known as pseudosuchians dominated the planet. These ancient creatures, distant relatives of modern crocodiles, came in a wide variety of shapes and sizes. They dominated the ecosystems of their time, occupying the niches of top predators and large herbivores. Lurking in the rivers and lakes were enormous phytosaurs, strikingly similar to crocodiles but actually belonging to a completely different branch of reptiles. These aquatic predators were the true kings of freshwater bodies. On land, however, reigned the eddosaurs, clumsy herbivores covered in solid, heavy armor like living armored vehicles. They were formidable, nearly invulnerable inhabitants of the prehistoric plains. And then came the Rawisuchians, fast, strong, and merciless hunters. These carnivorous reptiles struck terror into all living things, often surpassing in size the first dinosaurs with which they shared the world. At this stage in history, dinosaurs were still too small and few in number to pose serious competition. They weren't yet masters of this land, but they were already confidently settling in, adapting and finding food where the larger reptiles didn't hunt. They could have been scavengers, small predators, or omnivores that didn't attract the giants' attention, but everything was already set for a radical change. This shift occurred approximately 201 million years ago, at the very end of the Triassic period, when the planet experienced another mass extinction event, known as the Triassic-Jurassic extinction. While not as devastating as the catastrophe that ended the Permian period, this event nonetheless caused colossal upheavals in the world of life. Scientists believe it was caused by a series of massive volcanic eruptions associated with the slow breakup of the supercontinent Pangea. These eruptions created what we now call the Central Atlantic Igneous Province, a vast area of volcanic rock that stretches across parts of modern-day North and South America, as well as Africa. These massive eruptions released unimaginable quantities of carbon dioxide and sulfur dioxide into the atmosphere. This triggered rapid global warming. The oceans became more acidic, and a cascade of environmental disasters was unleashed, pushing countless species to the brink of extinction. The dominant reptile groups of the late Triassic, pseudosuchians, atosaurs, phytosaurs, and rauisuchians, were particularly hard hit. Their reign came to an end. Although many were wiped off the face of the earth, dinosaurs, against all odds, largely survived. The mystery of their survival still baffles scientists. What was it? Perhaps it was their unique mobility, which allowed them to quickly find new food sources, or perhaps it was their omnivorous nature, their ability to feed on almost anything in a devastated world. Or perhaps it was sheer chance, blind luck, that decided everything. But whatever the true reason, the fact remains, most key dinosaur groups survived this catastrophe. With their main competitors vanished into oblivion, a whole new world opened up for dinosaurs. Now, nothing stood in their way as they grew, filled vacant niches in ecosystems, and evolved into a stunning diversity of shapes and sizes that still boggles the mind. And all of this happened in an incredibly short time frame by evolutionary standards, just a few million years. After the great extinction at the dawn of the Jurassic, the dinosaur world exploded with diversity. Gigantic sauropods emerged, long-necked titans of the plant world, their bodies reaching the length of a modern bus. During the supercontinent's era, animals were able to migrate freely across its entire territory. And today, paleontologists are finding irrefutable evidence of this. Fossils of creatures that once lived side by side are now found on continents separated by thousands of kilometers of hostile ocean. Take Mesosaurus, for example. It's a small freshwater reptile whose remains have been found in both South America and Africa. How is this possible, given the entire Atlantic Ocean separates these continents? The answer is simple. In Mesosaurus's time, there was no ocean between them. Or another example, Lystrosaurus, a bizarre pig-sized creature that combined reptilian and mammalian features. Its bones have been found in places as far apart as Africa, India, and even icy Antarctica. These finds provide compelling evidence that these lands were once a single entity, and animals roamed freely across it. The same applies to plants. One of the most striking examples is the prehistoric fern Glossopteris. Fossilized imprints of its leaves have been found in South America, Africa, India, Australia, and Antarctica. Today, the climates in these regions vary dramatically, from humid jungles to icy deserts. But in the distant past, they were all part of a single ecosystem, Pangea, where this fern thrived. Simultaneously, ferocious theropods emerged, predators that became the ancestors of later nightmarish giants like Tyrannosaurus rex. This was the true beginning of the age of dinosaurs. However, The origins of this dominance lie in the Triassic period. It was not simply a time of survival, but a crucial turning point in the annals of life on our planet. Imagine the Triassic as a gigantic natural testing ground where dinosaurs, the first mammals, and countless other creatures began their long and winding evolutionary journey. Thanks to paleontological discoveries around the world, our knowledge of this era has expanded beyond recognition. Let's move on to Argentina. Here, in the Ixigualasto geological formations, some of the finest specimens of the oldest dinosaurs to ever walk the earth have been found, including pioneers like Herrerasaurus and Eoraptor. And in South Africa, the earth has yielded fossils of ancient synapsids, such as cynodonts, creatures that were close relatives of mammals. These creatures, which lived during the Triassic, play a key role in understanding the gradual transition from reptile-like ancestors to true warm-blooded creatures. A veritable treasure trove of Triassic reptiles has been discovered in the Chinle Formation of North America. This discovery allows us to study in exquisite detail the amazing and diverse animals that inhabited the planet during those distant times. Every fossil find, whether a single tooth or a complete skeleton, adds a new, invaluable piece to the puzzle of our understanding of this fascinating era. Researchers constantly return to old data, but with new tools. Modern technologies such as computed tomography and sophisticated computer modeling allow them to peer inside fossils and learn more than ever before. The Triassic period provides a striking example of life's astonishing ability to recover, adapt, and thrive, even after the most devastating catastrophes in Earth's history. It was a time of new beginnings, a time when life essentially started over. While tiny mouse-like mammals were taking their first tentative steps, dinosaurs were already confidently advancing to their absolute dominance, laying the foundation for the next 135 million years of life on Earth. Now imagine a world so unified and vast that one could theoretically walk from the South Pole to the North Pole without ever having to wet one's feet in the ocean. This isn't science fiction. This was the incredible reality of Pangea, the gigantic supercontinent that shaped our planet for hundreds of millions of years. This astonishing time spanned hundreds of millions of years, from the twilight of the Paleozoic era to the dawn of the Mesozoic era. Pangea wasn't just a collection of continents. It represented virtually all of Earth's land mass, fused into a single massive block. Its colossal size not only reshaped the planet's geography, but also profoundly impacted the functioning of the entire Earth system, especially climate. In our modern world, we're accustomed to the Earth being divided into continents and oceans, each with its own unique climate. But during Pangea, when this supercontinent was united, everything was completely different. Pangea created its own unique climate system, strikingly different from anything we observe today. While its ocean-washed fringes were mild and humid, its interior was a scorching, dry, and unforgiving desert. Understanding Pangea's climate is more than just a glimpse into ancient weather. It's a powerful demonstration of how the arrangement of land and sea can have a profound impact on winds, precipitation, ocean currents, and ultimately, life itself. But the most striking feature of Pangea's climate was its core. Imagine a land so vast and deep that even the most humid ocean winds couldn't carry their life-giving moisture. After traveling thousands of kilometers, all the water evaporated long before reaching the center. By the time these winds reached the heart of the continent, they were dry and hot, unable to bring a single drop of rain. As a result, the center of Pangea was in a constant state of extreme drought. And this wasn't just any desert, it was a super desert, stretching across what are now parts of North America, South America, and Africa. These lands were covered in gigantic sand seas, with massive dunes that rolled endlessly in the hot winds. Between the dunes stretched dry salt flats and seasonal lakes that would briefly fill with water during the rarest of rainstorms, but then quickly evaporate under the scorching sun. And the scorching sun left behind only a thick crust of salt and minerals. The air was thick with dust and often tinted red by tiny iron particles in the soil. The minerals, literally rusted by the perpetual drought, gave the region its characteristic reddish hue. In those distant times, the air was incredibly dry. We know this thanks to geologists who have discovered thick layers of reddish rock on many modern continents. These rocks, known as red beds, are irrefutable evidence of ancient aridity and intense heat. Even the hardiest plants and animals that inhabited those conditions had to adapt to this arid climate. Ancient conifers and cycads grew waxy leaves that helped retain moisture and deep roots that desperately sought out hidden water sources underground. The creatures that lived there were equally resilient. Their bodies were perfectly adapted to survive in conditions of constant water shortages. The sheer size of Pangea made this dry zone truly gigantic. Separated from the ocean, it created an isolated climate system, barred from moist air. But if you traveled from this scorching desert to the coast, you would find yourself in a completely different world. Thanks to the Panthalassa Ocean, which surrounded the continent, and the large Tethys Ocean, which cut into it on one side, the coastal regions enjoyed much more pleasant weather. These areas, which would later become parts of Europe, Asia, and Australia, enjoyed high humidity, regular rainfall, and a milder climate. Temperature fluctuations here were minimal. The proximity to the ocean meant the air was saturated with moisture, which often fell as rain, creating lush landscapes full of forests, rivers, and swamps. And we have ample evidence of this. Massive coal deposits formed during the Carboniferous and Permian periods, just as Pangea was forming, confirm this. These ancient coal seams are nothing more than the remnants of vast tropical forests that once covered the warm, humid lands along the edges of Pangea. Giant club mosses, ferns, and horsetails blanketed the land, absorbing the rain and transforming into dense, impenetrable jungles. It was this jungle that later turned into the coal we use as fuel today. Just offshore, the oceans teemed with life. Fossils of sea creatures, coral reefs, and shell deposits along ancient coastlines testify to a healthy and vibrant marine environment. Ocean currents, though their exact routes are still debated, help transport heat and moisture across the supercontinent, making life along the coast incomparably more comfortable and diverse than in the arid center. Thus, during the Pangea era, Earth was a planet of striking contrasts. Its enormous size and unique shape created a world with deadly dry deserts at its center, surrounded by lush vegetation and verdant shores at its edges. It was a wondrous creation, shaped by the great forces of land, sea, and air. Pangea serves as a stark reminder that the arrangement of the continents is more than just a detail for cartographers. It is one of the key factors determining the climate and life itself on the planet. One of the most impressive and mysterious phenomena of Pangea was the gigantic seasonal weather cycle known as the supercontinent monsoon. Today, monsoons are seasonal winds that arise from the differential heating and cooling of land and ocean. However, during Pangea, this natural effect was amplified to an almost unimaginable scale, as the landmass was incredibly vast. During the summer months, the vast interior of Pangea heated significantly faster than the surrounding ocean, Panthalassa. The land became as hot as a giant frying pan. Imagine a world where geography itself dictated the rules. Imagine while the global ocean retained its protective coolness, the giant supercontinent of Pangea became a scorching frying pan. This created a colossal contrast in atmospheric pressure. A low-pressure area formed over the sun-baked interior, a veritable funnel, sucking in air. At the same time, a high-pressure zone dominated the much colder ocean expanses. This incredibly powerful differential forced gigantic, moisture-laden air masses from the ocean to rush inland. This clash of the elements resulted in monsoon downpours of unprecedented intensity. The skies literally opened, unleashing torrents of water upon Pangea that continued for days on end. The scale of these rains was truly titanic, far surpassing any modern tropical storm. Moisture-laden winds brought merciless summer floods to many corners of the southern continent, striking coastal areas with particular devastation. Rivers turned into raging torrents, sweeping away everything in their path. Entire regions were submerged, and even lands far from the coast felt the destructive power of this watery force. In a short period of time, so much precipitation fell on land that the sun-baked plains were transformed, covered in lush greenery, at least for a time. But with the arrival of winter, the entire picture changed completely. The vast landmass cooled much more rapidly than the ocean, and the air above Pangea became cold, dense, and heavy. This created a powerful high-pressure system over the continent, while the ocean, retaining heat, turned into a low-pressure zone. Now, everything was different. Icy, absolutely dry winds blew from the depths of the continent toward the sea, establishing a harsh and merciless climate. A dry season gripped much of Pangea in a death grip. These whiplash-like seasonal swings, from a global flood to a devastating drought, had a colossal impact on the appearance of the entire planet. This endless cycle of wet and dry seasons left its mark on the Earth's geological record. During the rainy season, rivers carried tons of sediment, which were deposited in layers, a layer of coarse particles, then a layer of fine particles. These geological formations, known as rhythmites, became a kind of natural calendar, marking the changing seasons. Ancient soils, which paleontologists call paleosols, also contain invaluable information about the vegetation and climate of that distant era. They show clear traces of alternating periods of total moisture and severe drought. Fossilized plants found in these regions complete the picture. Many species developed amazing adaptations to survive the long dry months and thrived as soon as the saving rains returned. This is a striking example of how life adapted to a truly extreme climate. Pangea's supermonsoon system was so massive that its influence wasn't limited to a single region. It determined weather patterns across much of the planet, acting as a global climate driver far more powerful and pervasive than the monsoons we observe today. However, this wasn't the only climatic miracle associated with Pangea. Around the same time this supercontinent formed, Earth plunged into a massive ice age known as the Carboniferous glaciation. And this wasn't just a brief cooling episode in a single region. No, it was a planetary event, burying vast swaths of land beneath kilometers of ice. This great ice age began over 300 million years ago. At that time, the enormous southern supercontinent of Gondwana, which encompassed what would become Africa, South America, Antarctica, Australia, and India, slowly drifted over the South Pole. Once these colossal land masses found themselves at the coldest point on the planet, an unstoppable process began. Snow fell and fell, but the short summers did not melt it. Year after year, century after century, the snow cover grew thicker, compressed under its own weight, turning into massive glaciers and ice sheets. But there was another important reason for this ancient cooling, a sharp drop in atmospheric carbon levels, which led to a decrease in carbon dioxide concentrations. During the Carboniferous period, vast forests spread across the planet, which would later form gigantic coal deposits. These trees and plants absorbed carbon dioxide as they lived. When they died, their remains were buried deep underground, taking with them enormous amounts of carbon, which became locked in a geological trap. Atmospheric CO2 levels plummeted, the greenhouse effect weakened, and Earth's temperature began to drop, creating ideal conditions for further glacier expansion. Other factors also played a role. As the continents shifted and collided, ocean currents changed. Some sea passages closed, disrupting the global distribution of heat across the planet and allowing ice to accumulate even more rapidly near the poles. Evidence of this ancient glaciation is found all over the world, especially on all the continents of the southern hemisphere. Geologists, like detectives reading a rock record, are discovering tillites, special rocks formed from debris dragged along by glaciers. In many places, they find rock surfaces scarred by glaciers as if a giant plow had gouged the stone. The slow but inexorable movement of the ice sheets carved characteristic U-shaped valleys into the landscape. Enormous boulders, shed from melting icebergs, also left their mark, further evidence of the ice's former grandeur. Millions of years later, Pangea began its slow northward journey. The ice sheets began to melt, and the planet entered a warmer phase that encompassed the Triassic and Jurassic periods. This story clearly demonstrates how complex and unpredictable our planet's climate system can be. It is influenced by continental movements, changes in atmospheric composition, and even the Earth's orbit around the Sun. Pangea affected more than just land and ice. It completely reshaped the behavior of the oceans and atmosphere on a global scale. This single landmass was surrounded by the Panthalassa Ocean, a vast, boundless expanse of water that covered most of the planet. Pangea also became the stage for one of the most horrific events in Earth's history, the Permian-Triassic extinction event, sometimes called the Great Dying. This catastrophe occurred approximately 252 million years ago and wiped out nearly 96% of all marine species and about 70% of terrestrial vertebrates. Scientists still debate the exact causes of this apocalypse. Some blame the monstrous volcanic eruptions in Siberia, which spewed billions of tons of ash and gases into the atmosphere. Others believe the extreme climate conditions on the supercontinent itself were to blame. Most likely, it was a deadly combination of both factors. Even after its demise, the ghost of Pangea continued to shape the world. As the continents drifted apart, new conditions for life emerged. New mountains and coastlines emerged, and climates shifted. Living organisms were forced to adapt to these endless changes. New species emerged, capable of surviving in isolated worlds, leading to a veritable explosion of plant and animal diversity. In essence, Pangea shaped many features of the modern world: the layout of the continents, the contours of mountain ranges, ocean currents, and even the animals and plants found in different parts of the globe. All of this is an echo of the distant past. This story also reminds us that our planet is a living, constantly changing organism. Pangea wasn't the first supercontinent, and it certainly won't be the last. Unlike modern oceans, which are divided into basins, Pangea was a single, unified entity. The lack of continental barriers allowed gigantic ocean currents to circulate freely across the globe. This likely made the deep-sea circulation system in some regions simpler and more stable. Off the eastern coast of Pangea lay the Tethys Ocean, a warm, shallow sea that acted as a giant heat accumulator. It played a key role in regulating temperature and mixing its waters with those of the larger Pangea Ocean. The interaction between these two bodies of water generated unique and powerful ocean currents, the likes of which simply do not exist today. The scene in the air was no less unusual. Basic principles of atmospheric circulation, such as the updrafts and downdrafts we know today as Hadley cells, still existed. But the enormous landmass of Pangea made the climate even more extreme and unpredictable. Over such a vast territory, seasonal high and low pressure systems were much more pronounced, generating hurricanes of monstrous strength. Because Pangea lacked many of the mountain ranges that would form later, these giant winds encountered no obstacles. This allowed air masses to travel unimpeded over vast distances. Climate change in one corner of the supercontinent could reverberate in areas thousands of kilometers away. This effect is known as teleconnection. For example, a change in the strength of the monsoon in one place could dramatically alter precipitation patterns on the opposite side of the continent. The Pangea Ocean, with its boundless expanse and colossal moisture reserves, made the contrast between the humid coastal zones and the arid interior even more striking. The coasts of Pangea were lushly verdant, while its core was a harsh, arid desert, especially in winter. This unique climate, with its unbearably hot summers, freezing winters, powerful monsoons, and periods of glaciation, had a profound impact on the evolution of life. Plants and animals in desert regions developed incredible mechanisms for surviving in the face of water scarcity, while the rain-drenched coasts supported rich ecosystems teeming with a wide variety of species. With no ocean barriers between continents, animals and plants could migrate freely over vast distances. This resulted in a more homogeneous world with less regional diversity than we see today. But the story of Pangea isn't just a gripping saga of how disparate land masses came together. It's also a tale of how, over time, this colossus was torn apart. Like the great supercontinents that came before it, Pangea wasn't eternal. It was destined to slowly but inexorably disintegrate under the influence of powerful invisible forces hidden deep within the Earth. These forces, which we now call plate tectonics, are continually and inexorably reshaping our planet. However, Pangea didn't collapse overnight as a result of some sudden catastrophe. Its disintegration was a slow, drawn-out drama that stretched over tens of millions of years. This long divorce began approximately 200 million years ago, at the end of the Triassic period, and continued throughout the Jurassic. The first signs of the coming changes were barely noticeable. The Earth's crust began to sense pressure building deep beneath it. Then the planet's surface began to bulge slightly, as if some incredible force were building up beneath it. And finally, the crust gave way and began to crack, forming gigantic faults. Before us are rift valleys, giant, deep scars that stretch across the entire surface of the ancient supercontinent. To understand how our modern world is structured, why the continents and oceans look the way they do, we must look into the past and unravel the mystery of the breakup of the great Pangea. Ancient cracks left by this catastrophe can still be found in rock formations across the globe. They are like frozen chapters in the planet's stone chronicle. These geological clues allow scientists to piece together the dramatic story of how the lands we now inhabit were once a single whole and then mercilessly torn apart. But what causes these colossi, assembled with such incredible force, to ultimately crumble to dust? This question plunges us into the very heart of planetary mechanisms. Deep beneath our feet, in the Earth's mantle, movement never ceases. Enormous currents of molten rock slowly swirl in gigantic convection cells like water in a vast boiling cauldron. These currents are one of the main driving forces behind the continents. There's a compelling theory that explains why supercontinents are destined to break apart. It's known as the insulator effect. Imagine Pangea as a gigantic, impenetrable blanket that covered a vast swath of the planet. Acting as such a massive shield, it effectively trapped a colossal amount of heat rising from the Earth's core. This heat was generated by the slow decay of radioactive elements trapped deep within the Earth's core. Over millions of years, like steam under a cauldron's lid, this heat accumulated beneath Pangea's crust. The mantle beneath it grew hotter and lighter. The superheated material began to bulge, pressing on the crust from below, causing the landmass to buckle and stretch. And, like rubber stretched to its breaking point, the crust gave way. It began to crack, and the first fissures began to appear across its surface, ominous harbingers of the coming breakup. But that's only part of the story. A crucial role in this process was played by so-called mantle plumes, giant columns of molten rock that rise from the very depths of the planet, possibly from the very core mantle boundary. When such a plume reaches the base of the Earth's crust, it creates a hot spot, a place where volcanic fury can erupt to the surface. These plumes carry not only heat, but also incredible pressure, forcing the crust to rise even higher and making it even more fragile. One of the most spectacular examples of such activity occurred approximately 200 million years ago. This was a massive volcanic event known as the Central Atlantic Igneous Province, or CIMP for short. It occurred just as the young Atlantic Ocean was just beginning its journey. CIMP was one of the largest lava flows in the history of the planet. Millions of cubic kilometers of igneous rock gushed to the surface, drenching vast areas that today comprise North and South America, Africa, and Europe. The scale of this catastrophe suggests that it was caused by one or even several powerful mantle plumes. This fiery apocalypse likely served as the final blow that finally weakened the shell of Pangea and helped the continents begin their great divergence. In today's world, the movement of tectonic plates is largely determined by forces that weren't present at the dawn of Pangea's breakup. For example, so-called slab pull, when a heavy oceanic plate sinks into the mantle, or ridge spreading, when new crust is born at mid-ocean ridges. But in the early stages of a supercontinent's collapse, the most devastating force came from within. It was the heat rising from the depths that literally pushed the continents apart, paving the way for future oceans. The first steps of this process, known as rifting, were not instantaneous. Oceans did not form overnight. It all began with a slow but inexorable bulge of the Earth's crust. As hot mantle material rose from below, the land slowly rose, forming colossal, sweeping plateaus. The first cracks began to appear in this taut shell. Over time, these developed into a network of faults, along which giant crustal blocks moved like piano keys. The blocks that were pushed down formed grebens, elongated, low-lying valleys, while the uplifted blocks became ridges that rose along the edges of these valleys. These grebens were the first rift valleys, the first clear signs that Pangea had begun its journey to oblivion. As the crust stretched and thinned, the pressure on the mantle beneath it eased. This drop in pressure caused mantle rocks to melt, forming magma. This molten rock, lighter than the surrounding material, rushed upward through cracks, triggering monstrously powerful volcanic eruptions. As a result, entire oceans of lava, known as trap basalts, poured onto the surface. They covered vast territories, creating dark, lifeless, rocky plains. The most striking example of this is the CIMP province, where vast fields of solidified ancient lava can be seen to this day. These eruptions are clear evidence of the colossal amount of heat erupting from the Earth's interior, a sure sign of a major geological upheaval. It was in these scars, in places where Pangea was cracking at the seams, that the modern oceans were destined to be born. One of the key faults was the Central Atlantic Rift System, where the Atlantic Ocean first began to open. This gigantic rift arose between what would become North America and Africa, and then, like lightning, spread southward, separating South America and Africa and giving birth to the South Atlantic Rift System. But it wasn't an instantaneous rupture. At first, it was just a chain of discontinuous basins, long, narrow valleys that stretched for hundreds of kilometers. Only over millions of years did these basins gradually connect and widen, becoming an ocean. Some of these ancient rift valleys remain to this day. For example, the Newark supergroup in the eastern United States. Here, we see layers of fluvial and lake sediments mixed with lava flows and volcanic ash, the rocky evidence of the Earth breaking apart. A similar process occurred further south, eventually separating South America and Africa. Want to see this monumental process in action today? Just look at a world map and find the East African Rift System. This is where the African continent is literally tearing itself apart right before our eyes. In East Africa, we see all the same signs: vast tracts of uplifted land, deep faults, chains of active volcanoes, and elongated lakes filling valleys. It's a veritable living geological laboratory, demonstrating that the same forces that once destroyed Pangea continue to work to this day. It's worth noting, however, that not every rift is destined to become an ocean. Some, having begun to diverge, stop for some reason. These failed rifts, or aulacogans, are like forgotten scars on the Earth's crust. They are places where destruction began but was never fully completed. Over time, these failures fill with thick layers of sediment and can sometimes be revived by new tectonic forces. Some of these failed rifts play an important role in the modern world. For example, the West African Rift turned out to be a failed offshoot of the South Atlantic Rift, and in the central United States, there is an ancient rift that is the remnant of a rift associated with an even older ocean that existed long before Pangea. These failed rifts, like time capsules, preserve the history of Earth's past and often conceal vast oil and gas reserves. The story of Pangea's demise is written in stone across the entire surface of our planet. Geologists study it from a multitude of clues, and one of the most important keys to this mystery lies in the rocks left behind, in the very deep cracks and valleys that formed when the supercontinent broke apart. These valleys, like milestones in Earth's history, allow us to peer into the very heart of planetary processes. So-called rift valleys began to form as the Earth's crust stretched. Sinking ever deeper, they created vast basins that immediately began to fill with silt, sand, and gravel, carried by rivers and streams. Over time, kilometers of sedimentary rock accumulated in these valleys. Ancient rivers and lakes left behind layers of sandstone, shale, and conglomerate. One of the most distinctive features of these deposits are the so-called red layers. Geologists distinguish them by their rich reddish color. This coloring is imparted to the rocks by iron minerals that simply rusted in the open air. Their color is a direct indication of the climate of that era: hot, arid, similar to modern deserts. And in places where the waters of the young ocean occasionally penetrated and then evaporated under the scorching sun, thick layers of salt deposits formed. These include layers of halite, better known as rock salt, and gypsum, a soft mineral we use in construction. Imagine an ancient world where the landscape lives in a perpetual rhythm. First, it is flooded by shallow seas, and then the scorching prehistoric sun evaporates the water to the last drop. This process, repeated over and over for millennia, resembled a gigantic natural saltworks. Where the reservoirs had dried up, thick, multi-meter-thick layers of salt and minerals remained. But these salt sheets are more than just a geological marvel. They played a key role in the formation of our planet's riches. Acting as an impenetrable lid, they sealed ancient organic deposits, which over time turned into priceless reserves of oil and natural gas. However, one shouldn't think that all these faults in the Earth's crust were parched deserts. In places where moisture reached, or during periods when the climate was more rainy, the picture changed dramatically. Here, in these rift valleys, lush life flourished. Vast swamps arose covered with dense, lush vegetation. Over millions of years, the remains of these ancient forests accumulated, compressed under the weight of new sediments, and eventually turned into thick seams of coal. This is clear evidence that even in the midst of tectonic upheavals, life found a way to thrive. But perhaps the most fiery and irrefutable proof of the great rift of Pangea is the igneous rocks born in the very heart of the earth. Imagine, the earth's crust is stretched, becoming ever thinner like a taut fabric, and at some point it gives way. Molten rock rushes upward from the depths of the mantle. It erupts to the surface not simply through volcanoes, but through gigantic fissures, pouring out fiery rivers. These colossal lava flows covered millions of square kilometers, solidifying and turning into endless fields of dark volcanic rock, basalt. Other giants existed before it, such as Rodinia and Columbia, and geologists predict that in the distant future, hundreds of millions of years from now, the continents may converge again, forming an entirely new supercontinent. Studying Pangea is like stepping into a time machine. It helps us understand not only the ancient past, but also the dynamic, ever-changing nature of our world, the planet we call home. Pangea reveals how everything in this world is interconnected, and how even the largest continents are merely temporary participants in an endless and beautiful cycle of creation and destruction. For almost all of human history, people have looked at world maps and seen something immutable, something eternal. The very idea that entire continents, those vast land masses on which we live, could slowly drift across the planet's surface once seemed so incredible that leading minds of the time simply laughed at it or vehemently rejected it. However, what was once considered absurd today forms the foundation of our understanding of geology, the theory of plate tectonics. It helps explain many mysterious phenomena on Earth. Let's fast forward millions of years to an era when only one gigantic continent existed on our planet, Pangea, and at its very heart, mountains towered. But these weren't just any mountains. They were veritable stone giants. These rock sheets, stretching across entire continents, are one of the most spectacular spectacles ever created by nature. We can still see traces of these titanic eruptions today. Vast igneous provinces like the Central Atlantic, the Pyrenees at the junction of South America and Africa, and the Karoo Plateau in southern Africa, all bear the scars of those majestic lava flows. Sometimes these fiery rivers were so powerful and cooled so evenly that nature, like a great sculptor, carved perfect hexagonal columns from the solidifying lava. These landscapes, known as columnar joints, look as if the giant pipes of some underground organ have erupted to the surface. But what we see on the surface is just the tip of the iceberg. Below ground, the molten magma behaved differently. It forced its way through cracks in the rock, spreading sideways and rushing upward. This is how unique geological structures were formed. Vertical walls known as dikes and horizontal layers called sills. This entire network resembles the frozen bloodstream of a rift zone, a complex system of conduits through which molten rock once flowed. By analyzing the chemical composition of these volcanic rocks, scientists can, like detectives, trace the path of the magma and understand from what depths it arose. This is the key to understanding the processes raging in the depths of our planet. Most often, it turns out that the magma originated directly in the Earth's mantle, which rose to the surface due to the stretching of the continental crust. At the geological structural level, the main sign of rift formation is so-called normal faults. These are giant cracks in the Earth's crust, along which one block of rock sinks while another remains in place or rises. This creates a stretching effect, a pulling apart of the Earth's surface. These faults are visible on geological maps, but an even more impressive picture is provided by seismic exploration, a method that uses sound waves to peer deep into the Earth. Using this method, scientists have discovered classic rift structures, down-thrown blocks, called grabens, and up-thrown blocks called horsts, which form when the crust cracks at its seams. Today, many of these ancient rift valleys are hidden from our view, buried beneath kilometers of younger sedimentary rocks. But even through this veil of time, modern geophysical instruments, such as gravimeters and seismographs, allow us to study their structure. We can see these ancient scars and draw conclusions about the titanic forces that once shaped the face of our planet. Seafloor studies have yielded another discovery. Oceanic crust is much thinner than continental crust. Another astonishing piece of evidence comes from paleomagnetism, the science that studies Earth's ancient magnetic field. This creates a kind of biological chronology that perfectly matches the geological record. Finally, the culmination of this process occurs. The continental crust can no longer withstand the stress and splits completely. Magma from the mantle no longer simply fills the cracks. It begins to form entirely new oceanic crust. The birth of a new ocean begins. A perfect example of this process, which we can observe right now, is the Red Sea. This long, narrow gulf between Africa and the Arabian Peninsula is actually a young ocean in its cradle, a modern rift zone where the Earth's crust is actively expanding. The geological forces at work on our planet are truly staggering. The breakup of the supercontinent Pangea was one of the most monumental events in Earth's history. This process wasn't instantaneous. It spanned tens of millions of years. It all began with the slow stretching and cracking of the Earth's crust, resulting in the formation of rivers and lakes in the troughs and depressions. Then came the Age of Fire. Volcanic eruptions drenched vast territories with lava, and future coal seams slowly accumulated in the swampy lowlands. It was a time of incredible tension, fire, and great change. Today, we find evidence of this drama all over the world. Twisted and torn rocks, giant faults, volcanic fields, and, of course, fossils of identical species found on different continents. These geological scars are nothing more than the imprints of a slow but inexorable process that has forever changed the face of our planet. This dramatic breakup of the continents serves as a constant reminder. The Earth's surface is never static. The continents continue their eternal dance, drift apart, and sometimes collide again in an endless tectonic cycle. Our planet is always in motion, and it holds the memory of Pangea deep within its fiery core. Imagine our Earth not just as a cold, motionless ball of stone, but as a living, breathing giant with a fiery heart and an indomitable spirit. Deep beneath our feet, in the very belly of the planet, powerful forces are at work, continually reshaping the world on the surface. For hundreds of millions of years, continents have traveled across the globe like giant pieces of a slowly moving puzzle. Sometimes they crash together, forming colossal supercontinents like Pangea. And sometimes they shattered with devastating force, giving birth to new oceans and forever redrawing the map of the world. But what incredible force can cause something as vast and solid as a continent to move, split, and change so dramatically? What mysterious mechanism lies hidden beneath the earth, invisibly shaping the destinies of entire continents? Many scientists believe the answer lies deep within the earth, in gigantic flows of molten magma known as mantle, plumes, or hotspots. These geological phenomena are no coincidence. They are truly internal furnaces of our planet, thermonuclear flares that radiate colossal amounts of heat rising from the very depths. This thermal radiation provides us with the key to understanding how and why the Earth moves beneath our feet. To better understand these mysterious forces, let's journey into the depths of our planet. Far below, beneath the mountains and oceans, the world is not as calm and stable as it appears from the surface. The Earth's interior is a seething cauldron of heat and incredibly slow, yet constant movement. Between the solid crust and its super-hot, liquid outer core lies a massive layer we call the mantle. This layer extends thousands of kilometers deep and on geological timescales behaves not like solid rock, but rather like a very thick, viscous liquid. The mantle is in constant motion, a process called convection. Imagine a huge pot of thick stew simmering on the stove. The hot stew rises from the bottom and cooler layers from the surface sink to take its place. The same process, only on an unimaginable scale, occurs deep within the Earth. Hot mantle material rises from the core, while cooler, denser material sinks back down. This perpetual mixing, lasting millions of years, is the engine of plate tectonics. Mantle plumes, or plumes, are giant columns of anomalously hot rock that rise up through this slowly boiling mass. Most geologists believe these plumes originate at a mysterious boundary deep within the planet, where the mantle meets the Earth's outer core. This hidden zone, located nearly 3,000 kilometers beneath our feet, is a veritable hellish forge. Temperatures here reach unimaginable levels, comparable to those on the surface of the sun. In this scorching region, some sections of the mantle become so superheated that they become lighter than the surrounding material. And then, like a hot air balloon lifting off and soaring into the sky, this giant bubble of superheated rock begins its long, upward journey. Imagine forces capable of moving entire continents, causing devastating earthquakes, and spewing fire from the planet's depths. Forces that erect colossal mountain ranges and determine the fate of all living things, from tiny plants to giant dinosaurs, dispersing them across the globe. This grandiose concept explains how our world works. According to it, the Earth's rigid outer shell, which scientists call the lithosphere, is not a monolithic shell. Instead, it is fractured into several gigantic rigid plates that float and slide across the planet's surface like pieces of a gigantic puzzle. These tectonic plates are in constant, albeit incredibly slow, motion. We can't see this process with our own eyes, as their speed is negligible, just a few centimeters per year. This is roughly the same speed at which our fingernails grow. Some of these colossal fragments support entire continents, while others form the floors of vast oceans. And when these titans collide, three main scenarios of geological drama unfold. The first scenario unfolds at divergent boundaries, where plates slowly move away from each other. As they move apart, molten rock, or magma, surges upward from the planet's scorching interior. It fills the resulting crack, solidifies, and creates new crust. This is how entire underwater mountain empires known as mid-ocean ridges are born in the ocean depths. A completely different picture emerges at converging boundaries in areas where plates collide. When two continental plates collide, their edges fold like paper and rise skyward, forming the world's greatest mountain ranges, such as the mighty Himalayas. But when an oceanic plate collides with a continental plate, the denser one begins to slowly subduct beneath the continent, plunging into the Earth's fiery mantle. This process creates the deepest oceanic trenches and gives rise to entire chains of fire-breathing volcanoes, shaking the planet with powerful earthquakes. And finally, the third type of interaction is transform boundaries. These are places where plates neither collide nor separate, but slide side by side, like two giant trains traveling in opposite directions. This sliding generates colossal stress along the fault lines, and when this stress suddenly breaks, a devastating earthquake occurs. One of the most notorious examples is the San Andreas Fault in California. But what drives these gigantic masses of rock? The answer lies deep beneath our feet, in the Earth's mantle. This is a layer of hot, viscous rock that is in perpetual motion. Imagine a giant pot of boiling soup. Heat from the planet's core warms the lower layers of the mantle, making them lighter and causing them to rise. At the top, they cool, become heavier, and sink again. These slow circular currents, called convection currents, act like a giant engine, slowly but inexorably dragging the tectonic plates on the surface. However, this brilliant theory didn't emerge overnight. The path to it was long and arduous, full of astonishing insights and fierce debates. In 1880, a man destined to change our view of the planet was born in Germany, Alfred Wegener. He was not a geologist by training, but his inquisitive mind and unusually keen eye allowed him to notice what others missed. Around 1912, Wegener presented to the world his revolutionary and daring idea, which he called the theory of continental drift. He simply looked at a world map and was struck by the obvious. The outlines of the east coast of South America and the west coast of Africa matched almost perfectly, like two missing pieces of a puzzle. This simple observation sparked a bold thought. What if these continents were once a single entity? And although scientists before him had also noted this strange similarity, it was Wegener who began systematically collecting irrefutable evidence from a wide variety of fields to prove that the continents were indeed in motion. He found some of the most powerful evidence in fossils, the frozen remains of ancient life. He discovered that the fossils of a small freshwater reptile called Mesosaurus were found in only two places on the planet, South America and South Africa. It was simply physically impossible for this animal to cross the vast Atlantic Ocean. The only logical explanation was that during the time of the Mesosaurus, the two continents were connected. And there's more. Wegener turned his attention to the fossils of land animals like Lystrosaurus and Cynognathus. Their bones were found on continents that are now separated by thousands of kilometers of water, including Africa, India, and even icy Antarctica. But perhaps his most famous discovery was the fossils of the ancient fern Glossopteris. Imprints of its leaves have been found throughout South America, Africa, India, Australia, and most astonishingly, Antarctica. The seeds of this plant could not have flown across oceans, and such a widespread distribution was only possible if all these lands had once been part of a single supercontinent. Wegener also peered into the silent language of rocks and mountains. They were not only incredibly tall, but also incredibly long, stretching for thousands of kilometers, like colossal barriers blocking the path of rain clouds into the interior. Here's how this eternal climate drama unfolded. Imagine moist winds carrying life-giving moisture from the ocean rushed toward the center of the continent. But in their path stood this impenetrable wall. The air masses had no choice but to ascend the slopes. As they rose, the air rapidly cooled, and all the accumulated moisture poured down as generous rain or snow onto the coastal slopes. As a result, the side of the mountains facing the ocean was immersed in lush greenery, turning into a veritable oasis of life. But once you crossed the ridge, the scene changed beyond recognition. A dry, scorching wind lashed the opposite side. Here lay a realm of perpetual drought, the so-called rain shadow, gigantic, sun-baked zones where precipitation was incredibly rare. These rain shadows didn't simply parch the earth. They were the architects of the greatest deserts our planet has ever known, stretching for thousands upon thousands of kilometers. The deserts at the very heart of Pangea were nothing like those we know today. Imagine boundless oceans of scorching sand, shimmering in every shade of red and gold, where fierce winds whipped up dunes as tall as multi-story buildings. In some places, the landscape might have resembled the modern Sahara or the Arabian Desert, but here the scale was truly planetary. He discovered that the Appalachian Mountains in eastern North America were virtually identical in structure and age to mountain ranges in Europe, such as the Caledonian Mountains. It was as if a single, gigantic mountain had been torn in half and pulled apart. These mountain ranges were composed of identical rocks and formed during the same ancient cataclysms, when the continents were still clenched into a single fist. As a final argument, Wegener drew on data on ancient climates. He found traces of gigantic glaciers in India, Africa, and Australia, places that today experience unbearable heat. This only made sense if these continents were once located much closer to the South Pole. Conversely, he discovered massive coal deposits in Antarctica. Coal, as is well known, forms from plant remains in hot, swampy jungles. This was irrefutable evidence that the icy continent had once been located near the equator, in warm latitudes. It would seem that the evidence was more than sufficient. But the scientific community of the time met Wegener's theory with hostility. Despite fossils, mountains, and climate data, most scientists refused to believe his idea. The main problem was that Wegener couldn't clearly explain the force that moved the continents. He suggested that the continents might break through the ocean floor, or that they were pulled along by the forces of the Earth's rotation and the Moon's gravity. However, physicists quickly calculated that these forces were negligible and incapable of moving such colossal land masses. Without a clear mechanism, his theory seemed like science fiction. Moreover, since Wegener wasn't a geologist by profession, many viewed him as an amateur, an upstart, meddling in areas that weren't his business. For many years, his brilliant idea, ahead of its time, was consigned to oblivion. But everything changed in the 1950s and 60s. A new era of research began, providing scientists with the missing clues and ultimately proving Wegener right. One of the breakthroughs was the discovery of seafloor spreading, or ocean floor spreading. Two scientists, Harry Hess and Robert Dietz, proposed that new oceanic crust is constantly being created at mid-ocean ridges. Molten rock rises from the mantle, cools, and slowly pushes older crust away from the ridge like a giant geological conveyor belt. But the most compelling evidence came from paleomagnetism, the study of Earth's ancient magnetic field. Scientists discovered that when lava cools, iron particles within it align like compass needles, pointing toward the magnetic pole. But Earth's magnetic field isn't static. It reverses polarity every few 100,000 years. Studying the ocean floor, the researchers discovered something astonishing. The rocks were arranged in bands of varying magnetization. One band had normal polarity, the next reversed, then normal again, and so on. These bands were perfectly symmetrical on either side of mid-ocean ridges, creating a kind of magnetic barcode. This was direct evidence that new crust was being born at the center of the ridge and was spreading outward in both directions. Later, seafloor drilling confirmed this hypothesis. The farther from the ridge the rock samples were taken, the older they were. Everything matched. Along with these discoveries, modern science was armed with new, powerful tools. Chief among these was the Global Positioning System, or GPS. Using a network of satellites orbiting high above the Earth, scientists were able to measure the movement of tectonic plates with incredible precision, down to the millimeter. Researchers placed GPS receivers around the world on different continents. These devices allowed them to observe their changing positions in real time. Although these shifts are tiny, they are constant and inexorable. The technology demonstrated, as predicted by plate tectonics, that the Earth's crust is indeed moving. In the face of this data, received from space, even the last skeptics who once scoffed at Wegener's ideas capitulated. But GPS isn't the only tool. Science has advanced greatly since the time of Alfred Wegener. Today, paleontologists use sophisticated dating methods to determine the age of rock layers with astonishing accuracy. This allows them to compare geological formations on one continent with their counterparts on another, proving that they were once a single entity. Imagine a journey into the very heart of our planet, into the fiery depths of its mantle. Here, under immense pressure, monstrous forces are born capable of reshaping the face of the world. Superheated rock, now slightly lighter and more flexible than its surroundings, begins its incredibly long and slow journey upward to the surface. But this ascent is not a chaotic process. On the contrary, it is strikingly orderly. The geological force known as the mantle plume takes on a shape eerily reminiscent of a giant mushroom. A long, slender tail extends from the very depths of the earth, crowned by a huge flattened head. This plume head is a formation of truly titanic proportions, its diameter reaching hundreds, sometimes thousands of kilometers. It stretches directly beneath the Earth's crust, beneath the rigid shell of our planet. And when this colossal mass of molten rock reaches the lower boundary of the lithosphere, the rigid outer layer comprising the crust and upper mantle, the real spectacle begins. First, the sheer monstrous pressure and heat from the plume begin to push solid rock upward. The lithosphere, like a giant carpet, slowly sags as if someone were pressing down on it with an invisible hand. A colossal bulge forms on the Earth's surface, a vast dome that can rise hundreds of meters, even a kilometer in height. This uplift strains the Earth's crust, making it thinner and weaker, like a rubber film stretched to its limits. Eventually, the strain becomes unbearable, and the stretched crust begins to crack. Deep, narrow scars appear on its surface, so-called rift valleys. These are places where the planet literally begins to tear itself apart. However, this is only the beginning of the cataclysm. The incredible heat emanating from the mantle plume literally begins to melt the rocks beneath the crust. This process creates an ocean of magma, molten rock. Because liquid magma is lighter than solid rock, it rushes upward, seeping through cracks and fissures in the lithosphere. This leads to volcanic eruptions of truly apocalyptic proportions. We're not talking about ordinary volcanoes spewing ash. No, these are colossal outpourings capable of covering entire continents with meters of boiling lava. Scientists call such formations large igneous provinces. Some of these ancient lava fields were so vast that they covered territories comparable to entire modern countries. For example, the famous Deccan traps in India or the Siberian traps in Russia are all believed to be the result of the ancient activity of giant mantle plumes. These formations, composed of thick layers of solidified lava, serve as silent witnesses to the unimaginable force slumbering within our planet's depths. This entire process, where heat from the depths causes the surface to bulge, crack, spew fire, and ultimately shatter, is more than just a beautiful metaphor. It's a real and fundamental mechanism that explains how supercontinents break apart. The rising plume weakens the Earth's crust from within, preparing it for a rupture. Then gravity takes over. Sinkholes appear on the slopes of the resulting dome, and the crust thins further, becoming vulnerable to any external force. Lava erupting to the surface further softens and lifts the soil, and eventually the entire region can be torn apart. In some cases, this leads to the birth of a new ocean, as the two halves of the former continent begin to separate, and new oceanic crust forms between them. The most iconic example of this monumental process is the collapse of the ancient supercontinent Pangea. Let's travel back 200 million years. Before us lies Pangea, a single landmass that united virtually all of Earth's continents. But beneath its mighty depths, a conspiracy was already brewing. It is believed that it was, at this time, that powerful mantle plumes began to rise from the depths. These plumes caused a vast uplift of the Earth's crust and triggered colossal volcanic eruptions. Unimaginable lava flows formed gigantic volcanic plateaus. The internal heat and this violent activity weakened Pangea's thick crust, leaving it defenseless against the tectonic forces that stretched and pushed it from various directions. Ultimately, the combination of internal heat and external stress proved fatal. Gigantic cracks formed, the continents began to drift apart, and the once unified Pangea began its long disintegration into the parts we know today. Thus, in a very real sense, the fire raging deep underground helped tear the supercontinent apart and continues to shape our planet to this day. So-called hotspots are merely the visible surface manifestations of something much deeper and more dramatic happening right beneath our feet. When a column of superheated material rises from the Earth's depths and begins to melt the solid layer above it, called the lithosphere, a persistent and long-lasting source of volcanic activity arises on the surface. And the most astonishing thing is that we can observe the consequences of this process. Many hotspots, such as the famous one beneath the Hawaiian Islands, have a unique feature. They remain virtually motionless deep in the mantle. Meanwhile, the surface of our planet, composed of giant tectonic plates, is in perpetual motion. When one of these plates slowly creeps over a stationary hotspot, its intense heat continues to burn its way upward, creating a chain of volcanoes, one after another, on the moving surface. The result is a chain of volcanic islands, where the youngest and most active volcano sits directly above the hotspot, while older, extinct volcanoes trail behind it like a trail. Imagine a conveyor belt slowly sliding over a blowtorch. The lamp stays in place, but as the belt moves, it leaves a long line of scorched marks. This is exactly what happens to volcanic chains. These hotspot marks provide scientists with invaluable information not only about how volcanoes work, but also about the evolution of our planet. They tell the story of how Earth's tectonic plates moved across the globe over millions of years. There is compelling evidence that mantle plumes originate from deep within the planet, far below the sites where most volcanic eruptions occur. But how exactly does volcanic activity help us understand global tectonic shifts? The answer lies in the scale, strength, and location of eruptions. Sometimes we observe massive lava flows that cover vast areas in just a few million years. In geological terms, that's practically a blink of an eye. These phenomena, known as basaltic floods, represent a special type of volcanism. Such eruptions are orders of magnitude more intense than the slow lava flows we see, for example, at mid-ocean ridges, or the explosive eruptions of cone-shaped volcanoes. Lava floods are a signal that something extraordinary is happening beneath the surface. Enormous emissions of heat and magma rise directly from the depths of the mantle, and that's not all. Chemical analysis of the lava erupted during these events can reveal much about its origin. Many of these lavas belong to a special category known as tholeiitic basalts. They form when rocks deep in the mantle melt much faster than rocks in the upper crust. This geochemical fingerprint helps scientists distinguish deep mantle eruptions from other types of volcanic activity. For example, silica-rich lava is more common in the crust. However, one of the most important clues is the location where these large-scale eruptions occur. If they occur far from tectonic plate boundaries, somewhere in the middle of a continent, it's a near certain sign that a mantle plume is at work. After all, the vast majority of volcanoes are located at plate boundaries, where they collide, move apart, or slide past each other. When volcanism erupts right in the center of a tectonic plate, it indicates that a powerful flow of hot magma has forced its way to the surface, uplifted the Earth's crust, and caused it to crack. This is precisely what happened during the early stages of Pangea's breakup. Around 200 million years ago, colossal lava flows erupted in areas that would later become parts of North and South America, Africa, and Europe. These flows became a dire omen for the entire planet, a signal that Pangea was beginning to disintegrate under the influence of internal forces. Typically, this process follows a clear pattern. First, the rising mantle exerts pressure on the lithosphere, causing the crust to bulge and stretch. This stretching leads to the formation of rift valleys, which resemble deep trenches or scars. Then, as the crust thins and the temperature beneath it rises, massive volcanic eruptions begin. Enormous masses of magma burst to the surface in the form of massive lava flows, creating a veritable fiery deluge. This intense volcanic activity marks the point of no return. The Earth's crust reaches a critical point, its structure begins to collapse, and all the conditions are in place for the formation of new ocean basins. In many cases, this fiery phase occurs literally just before the seafloor begins to diverge, marking the birth of a new ocean. This event can be compared to a grand fiery overture, a dramatic prologue that preceded the final breakup of the great continent. One of the most illustrative examples of this process is the Central Atlantic Igneous Province, known to paleontologists as the Camp. Let's fast forward 200 million years into the past. It was here, in this region, that a colossal eruption of molten rock occurred, flowing directly along the future fault lines. Those very scars on the body of Pangea, where the continent was already about to burst apart. The choice of location and timing for this apocalyptic event was far from random. It vividly demonstrates the inextricable link between the processes simmering in the Earth's molten interior and the global changes on its surface. We see a direct correlation between this monstrous volcanism and the titanic forces that ultimately pushed apart the tectonic plates and gave birth to the Atlantic Ocean. It was as if the planet itself were sounding a fiery alarm, warning of an impending tectonic shift destined to completely redraw the map of the world for millions of years to come. And even after the ancient supercontinent broke apart, mantle plumes and so-called hotspots continued their work. Tectonic plates, like giant rafts, continue their slow journey through these streams of molten mantle, leaving behind majestic chains of volcanic islands, such as those we see today in Hawaii. However, these island archipelagos are more than just a picturesque landscape. They serve as a kind of geological map, revealing with astonishing precision the trajectory and speed of plate movement over vast stretches of time. Each island, each seamount, is like a marker on the map, a piece of a giant puzzle that helps us piece together the story of the Earth's perpetual crustal movement. And yet, the story of mantle, plumes, and hotspots is only one of the many fascinating mysteries our planet holds. Hidden deep within the Earth is an incredibly powerful source of energy that, as it surges toward the surface, relentlessly shapes the shape of our world. These fiery pillars rising from the depths deliver enormous amounts of heat and molten rock to the planet's outer layers. This energy is capable of lifting and stretching the Earth's crust and ultimately, literally, tearing it apart. Massive volcanic eruptions, and especially the formation of large igneous provinces, are unmistakable signs that Earth is undergoing a period of profound transformation. These events are not random or uncommon. They are our planet's way of communicating with us, warning us that a supercontinent like Pangea is under enormous pressure and is about to be torn apart. This process will inevitably lead to the birth of new oceans and open a completely new chapter in the endless, ever-changing history of our world. Let's imagine a scene from the distant past, hundreds of millions of years ago. Almost all the land on our planet was gathered together, forming a single, gigantic supercontinent. This was Pangea, a truly colossal landmass, stretching from the icy silence of the South Pole to the frozen wastes of the North. This ancient world was home to parched deserts, where the earth blistered under the scorching rays of the sun, and mighty mountain ranges, now reduced to dust by time, towered high into the heavens. They stood as silent monuments to the epic collisions of continents that gave birth to this gigantic super-Earth. For most of the planet's ancient history, life flourished both on land and in the oceans. A world arose in which the very idea of continents slowly drifting apart seemed unthinkable. The planet's crust seemed immovable, and its continents were fused together. But deep beneath the surface, unnoticed by all life, forces of monstrous power were accumulating. Even nature's most magnificent creations are never eternal, and Pangea, for all its colossal scale, was no exception. This vast landmass was destined to break apart. Its slow and incredibly dramatic breakup became one of the most remarkable geological events our planet has ever witnessed. It was not an instantaneous cataclysm. The process stretched over millions of years, filled with tension and complex transformations. The key moment in this captivating saga was the birth of the Atlantic Ocean, which began with one of the most massive volcanic events in Earth's history, the formation of the very same Central Atlantic Igneous Province, or as it is also known, the Central Atlantic Ring of Fire. However, before we delve into this fiery beginning, let's back up a bit and look at how Pangea came into being in the first place. This supercontinent didn't appear out of nowhere. Over tens of millions of years, ancient continental plates collided and merged with each other like giant ice flows, eventually forming a single land mass. Approximately 300 million years ago, these collisions united almost all of Earth's land into a single, gigantic block. The emergence of the supercontinent Pangea had a profound impact on the planet's climate, the movement of ocean currents, and, of course, the entire course of evolution. However, beneath its massive cover lurked powerful, destructive forces. Deep within the Earth, heat constantly rose from the mantle, creating slow-moving currents of hot rock, like a thick stew in a boiling cauldron. These currents created enormous stress beneath the crust that made up Pangea. At some point, this stress became so intense that the surface began to feel pressure from within. At first, the signs of the coming changes were subtle. Pangea didn't explode or suddenly split apart. Instead, it began to slowly stretch, so slowly that the process would have been completely unnoticeable over a human lifetime. This early phase, known as continental rifting, was like stretching a thick piece of dough. At first, it simply thinned, then thinned in the middle, and finally, it tore apart. As Pangea expanded, the continental crust began to fracture. This rupture created a patchwork of long faults, and subsided valleys known as rift valleys and grebens. Grebens are areas of land that dip between two faults. They formed long, narrow basins that later became the cradle of the earliest Atlantic Ocean. Rivers rushed into these deepening cracks, carrying silt, sand, and other sediments. Over time, these materials accumulated layer upon layer, leaving behind a detailed geologic record of this dramatic period in Earth's history. But then came the moment of true geological spectacle, a powerful fiery event that transformed Pangea's slow stretching into a full-scale breakup. It was an incredibly powerful eruption in the Central Atlantic Magmatic Province, the one we know as the Camp. It became one of the most monumental volcanic cataclysms in the history of our planet. Around 200 million years ago, at the boundary between the Triassic and Jurassic periods, this catastrophic event occurred. The Camp, one of the largest volcanic provinces on the planet, became the site of the formation of endless fields of solidified lava. The timing of this eruption was no coincidence. It coincided almost perfectly with the moment when Pangea began to break apart and the Atlantic Ocean began to form. The scale of this eruption is staggering. Lava from the Camp province flowed across what are now North America, South America, Northwest Africa, and Southwest Europe. These four future continents, fused together at the time, witnessed this monumental event. All were part of a single entity known as Pangea. During the Camp's activity, scientists estimate that between 2 and 4 million cubic kilometers of magma were erupted. This amount of lava would have been enough to cover entire countries with a layer of solid rock several hundred meters thick. To grasp the scale of this phenomenon, imagine the 1815 eruption of Mount Tambora, the largest in human history. Now multiply its power by thousands, perhaps even tens of thousands. That's the colossal force we're dealing with. These eruptions didn't originate from tall, cone-shaped volcanoes, as we're accustomed to seeing in movies. Instead, they were massive outpourings of liquid lava from gigantic fissures in the earth. Huge flows of molten rock inundated entire landscapes, leaving behind massive layers of dark basaltic rock known as traps or flood basalts. Today, when scientists study lava from this region, they discover highly unusual chemical properties. A volcanic rock, known as tholeiitic basalt, is formed by the melting of material located very deep within the earth and rising to the surface. This type of lava indicates that the eruptions in the Camp region originated not at the surface, but at much deeper levels. They were most likely triggered by the upwelling of a massive mantle plume, a gigantic column of molten rock that rises from the planet's interior, melting everything in its path. When this plume collided with the lower crust of Pangea, it triggered intense melting, rock upwelling, and ultimately, these massive eruptions. Most of the lava from this area was erupted over a geologically short period of time, perhaps 1 to 5 million years. This concentrated volcanic activity occurred precisely at the time the Atlantic Ocean was just beginning its expansion. This suggests that the breakup of Pangea not only coincided with the emergence of the lamp, but was directly triggered by it. The incredible heat and pressure generated by the mantle plume's release weakened the Earth's crust, which was already thin due to stretching. It was like a powerful heat source acting on an already cracked sheet of glass. Eventually, It gave way. The earth fractured, and from this rift, a new ocean was born. Fast forward millions of years to a moment when planet Earth seemed to have reached its boiling point. Titanic forces had been accumulating within its scorching depths, and then, at one geological juncture, they broke free. This colossal release of energy literally tore the Earth's crust apart, marking the final and irrevocable end of the Pangea era. From that moment on, a single global continent no longer existed. A new era had begun, an era of drifting continents and boundless oceans, the very world we see today, forever changed by the forces that once split the greatest landmass in history. To truly understand the formation of the Atlantic Ocean, we need to imagine its progenitor, the so-called proto-ocean. This wasn't the mighty deep water world we see on maps. No, the proto-ocean was more like a newborn giant, just taking its first breath. It was a long, narrow rift, a gigantic fissure that bisected the face of the planet. At the very heart of this young ocean, life, geological life, was teeming. Here, brand new oceanic crust was being born. Molten rock, like the planet's blood, rose from the deepest depths, from the mantle. This flow of molten material cooled and solidified, forming the young ocean floor. This process is known to science as seafloor spreading. As the giant continental plates began to pull apart, the thick crust beneath them could not withstand the strain and finally cracked. Hot mantle from the lower layers of the earth poured into the resulting rift. Due to the sudden drop in pressure, it began to melt, forming new young crust right in the center of this tectonic scar. Thus, in agony, fire, and unbearable heat, new oceans are born. The ancient Atlantic, or Proto-Atlantic Ocean, most likely bore a striking resemblance to today's Red Sea. Imagine a long, narrow strait beneath which hot crust rages, while at its very center, furious volcanic activity rages. The emergence of the Atlantic Ocean was not an instantaneous event. It was a slow, gradual process. A rift began to form somewhere in the center of the future ocean, and then, over time, began to spread north and south. One of the first ominous harbingers of this monumental event was the formation of the Central Atlantic Igneous Province, a vast region engulfed in volcanic activity. This fiery province became the first true scar, the first deep fissure dividing the future North America on one side and the future Africa and South America on the other. As this rift grew wider and deeper, the Atlantic Ocean continued to expand. The process of seafloor spreading never stopped. New oceanic crust was continually formed along the growing rift, which we now know as the Mid-Atlantic Ridge. This ridge is essentially a massive underwater mountain chain that stretches across the entire Atlantic. Even today, it is still geologically active, continuing to create new seafloor, slowly but surely pushing the continents apart. We know this not from guesswork, but from a wealth of irrefutable evidence collected by geologists. One of the most compelling is the magnetic stripes imprinted in the oceanic crust. When new magma erupts at the center of a rift, as it cools, it records the direction of the Earth's magnetic field at that specific moment. But over millions of years, our planet's magnetic field has reversed its polarity many times. As a result, alternating bands of normal and reverse magnetism formed on the ocean floor. These bands, like a unique barcode, are perfectly symmetrically mirrored on either side of the Mid-Atlantic Ridge. They tell us the silent story of our planet's evolution, pinpointing exactly how, when, and where the seafloor formed. This allows us to create a detailed map of the ocean's growth. Other clues are hidden in the underwater topography, particularly in rift valleys, places where the Earth's crust has split apart. Patterns are also observed in marine sediments. They change from shallow to deep, clearly demonstrating how the ocean basin deepened as it grew. However, the birth of the Atlantic was more than just a geological event. It had catastrophic consequences for the climate and life on the planet. Eruptions in the central Atlantic province, which occurred approximately 200 million years ago, released unimaginable quantities of volcanic gases into the atmosphere, primarily carbon dioxide and sulfur dioxide. And these gases dealt a devastating blow to the biosphere. Carbon dioxide triggered powerful global warming. Sulfur dioxide, in turn, triggered chemical changes in the atmosphere, leading to acid rain and abrupt climate change. After a brief cooling caused by volcanic ash blocking sunlight, the world is likely significantly warmer than before. Many scientists believe this ecological crisis triggered the Triassic-Jurassic extinction event, one of the 5 largest mass extinctions in Earth's history. While experts still debate the exact sequence of events, the timelines are strikingly consistent. The planet's ecosystems were already fragile, and these monstrous eruptions may have been the final blow, wiping out countless animal species. In this sense, the birth of the Atlantic Ocean can be compared to the true end of the world. As the proto-ocean expanded, it changed the world not only climatically. Until this point, all oceans were part of a single, gigantic global ocean surrounding the supercontinent Pangea. But when the new ocean opened, it gave birth to an entirely new ecosystem. New ocean currents emerged, transporting warm water and influencing the global climate.